For centuries we have observed the nocturnal sky, attracted to the luminous, silent behemoth that governs our solar system, Jupiter. A planet of such immense size that it distorts the fabric of space itself. A realm of tumultuous tempests, overwhelming gravitational forces, and concealed seas beneath frozen satellites. It is an extraordinary planet, a cosmic powerhouse that influences the destiny of its surroundings. What genuinely resides beneath its tumultuous clouds? The Great Red Spot is a storm that has persisted for more than 3 centuries. Its magnetic field pervades space, releasing energy bursts more potent than those of the Sun. Its moons, some icy, others volcanic, harbor secrets that could transform our comprehension of extraterrestrial life. It was once referred to as the sovereign of the deities. Today, Jupiter transcends mythology. It stands as a mystery poised for revelation. Utilizing the most advanced telescopes and audacious space probe missions, we have unveiled the mysteries of the cosmos. Nevertheless, numerous inquiries persist. Is it possible that Jupiter was once a failed star? What mysteries does its metallic core harbor? Could its moon, Europa, possess an ocean abundant with extraterrestrial life? Prepare for a remarkable expedition to the most formidable, mysterious, and astonishing planet of all. This is Jupiter, the giant of the solar system. Jupiter, the largest planet in the solar system, is situated beyond the asteroid belt and is the 6th planet from the Sun. It is one of the brightest objects in the night sky. Only the Moon, Venus, and sometimes Mars outshine it. Ancient scientists named Jupiter after the Roman god of gods and the skies, not knowing its true size. However, the name is appropriate, as Jupiter is larger than all the other planets combined. The planet completes an orbit around the Sun in approximately 12 Earth years and rotates once every 10 hours, more than twice Earth's rotational speed. A small telescope can reveal its colorful cloud bands. Jupiter has a delicate ring system and more than 60 known moons, including one larger than Mercury and 3 that surpass the size of Earth's moon. Some astronomers believe that Europa, one of Jupiter's moons, might hide a warm water ocean and possibly some life under its icy exterior. Jupiter has a source of internal heat, releasing more energy than it takes in from the Sun. The interior pressure reaches a level that allows hydrogen to exist in a fluid metallic form. This enormous planet has the strongest magnetic field of all planets, showcasing a significant magnetosphere that, when viewed from Earth, is larger than the apparent size of the Moon. The system of Jupiter produces powerful bursts of radio noise, occasionally emitting greater energy than the Sun at certain frequencies. Even with its many remarkable features, Jupiter is mainly made up of hydrogen and helium, having an average density that barely surpasses that of water. The understanding of the Jovian System greatly improved after the mid-1970s thanks to the efforts of 3 spacecraft missions: Pioneers 10 and 11 from 1973 to 1974, Voyagers 1 and 2 in 1979, and the Galileo orbiter and probe, which arrived at Jupiter in December 1995. The Pioneer spacecraft served as forerunners to the Voyagers, showcasing that the radiation levels of Jupiter were controllable and outlining the main characteristics of the planet and its environment. The increased amount and intricacy of the Voyager instruments generated a wealth of new data. The analysis was ongoing when the Galileo mission commenced. Previous missions were solely flybys. However, Galileo dispatched a probe into Jupiter's atmosphere and subsequently entered orbit around the planet for thorough investigations of the entire system over multiple years. The Cassini spacecraft's 2000 flyby of Saturn and New Horizons spacecraft's 2007 flyby of Jupiter offered an additional perspective on the Jovian System. The journey to Pluto is underway. In 1994, observations of Comet Shoemaker-Levy 9's broken nucleus colliding with Jupiter's atmosphere provided insights into its composition and structure. Jupiter has an equatorial diameter of about 143,000 kilometers and orbits the Sun at an average distance of 778 million kilometers. The planet's low mean density is remarkable, especially compared to Earth's, with its significant size, mass, and short rotation period. The low density and substantial mass indicate that Jupiter's composition and structure are markedly different from those of Earth and the other terrestrial planets, a conclusion supported by extensive studies of the giant planet's atmosphere and interior. We have established 3 rotation intervals that are just a few minutes apart. The 2 intervals designated System 1 total 9 hours, 50 minutes, and 30 seconds. The average times for System 1, 9 hours 55 minutes 41 seconds, and System 2, 9 hours 55 minutes 41 seconds, show the speed of rotation at the equator and high latitudes, respectively, based on features found in the planet's clear cloud formations. Jupiter has no solid surface. The transition from the gaseous atmosphere to the liquid interior occurs gradually at considerable depths. The differences in rotation time across different latitudes do not suggest that the planet rotates at either of these average speeds. The actual rotation period of Jupiter is System 3, which is 9 hours, 55 minutes, and 29 seconds. The rotation period of Jupiter's magnetic field was first deduced from terrestrial radio data and subsequently confirmed through direct spacecraft measurements. Steady over 3 decades of observation, this period corresponds to the planet's significant interior, the source of the magnetic field, the atmosphere. A small telescope might uncover significant details regarding Jupiter. The section of the planet's atmosphere visible from Earth features different clouds positioned vertically and horizontally. Changes in these cloud systems can happen in just a few hours. However, a basic pattern of latitudinal currents has remained stable for decades. We typically use a standard nomenclature to describe the planet's appearance, referring to its alternating dark bands, belts, and light bands as zones. However, the essential trends exhibit greater resilience than this pattern. The Voyager probe sent back detailed pictures of Jupiter that showed different cloud formations with many elliptical features, which are similar to cyclonic and anticyclonic storm systems seen on Earth. All these systems are dynamic, appearing and disappearing over different time frames and geographic areas. The soft colors of the cloud layers show a range, starting with the warm yellow that dominates the top layer, moving through shades of brown and blue-gray, all the way to the famous pinkish hue of the Great Red Spot, which is Jupiter's largest, most prominent, and longest-lasting feature. Variations in the chemical makeup of clouds, which astronomers believe cause differences in color, are clearly associated with cloud systems' vertical and horizontal layering. We can compare the study of weather on Jupiter to the global patterns of air movement in Earth's atmosphere. On Earth, large spiral cloud formations often stretch across many degrees of latitude and are connected to the dynamics surrounding high and low pressure regions. The features of the Great Red Spot. Even with thorough observations from the Voyager and Galileo spacecraft, the true nature of Jupiter's unique Great Red Spot remained elusive at the start of the 21st century. The Great Red Spot has lasted for at least 300 years, aligning with extensive research on Jupiter, a planet whose cloud formations can alter in just a few days. Evidence suggests that the spot is slowly fading. However, a longer sequence of observations is necessary to confirm this claim. The dimensions are approximately 20,000 by 12,000 kilometers, 12,400 by 7,500 miles, large enough to encompass Earth and Mars. The significant size is what gives the feature its strength and distinctive color. The rotation period of the Great Red Spot does not match any of the 3 rotation periods of Jupiter. We have not yet successfully linked its variability with other phenomena on Jupiter. Voyager observations indicated that the substance within the area rotates counterclockwise every week, correlating with super-hurricane force winds of 400 kilometers, 250 miles per hour at the edges. The Voyager photographs captured numerous interactions between the Great Red Spot and much smaller disturbances occurring along the same latitude. The location's interior is remarkably calm, lacking signs of the expected upwelling or divergence of material from deeper layers. The Great Red Spot is a large anticyclone, a swirling vortex or eddy, with a diameter likely accompanied by considerable depth, allowing it to reach far beneath and above the main cloud layers. The decrease in temperatures and diminished gas absorption over the Great Red Spot suggests it is positioned higher than the main cloud layer compared to surrounding regions. Currently, observations of its inferior expansion are underway. These cloud systems show significantly reduced zonal confinement compared to those on Jupiter and shift based on latitude and longitude. The various features of the Earth's surface often affect the local weather conditions. In Jupiter's vast circulation, latitudinal currents dominate because the planet lacks a solid surface and distinct topographical features. Because there isn't a stable surface with clear edges and different heat-carrying regions, the flow of these currents and the clouds that form along with them are very important. The Great Red Spot, for example, moves in longitude concerning all 3 of the planet's rotational systems, but it stays fixed in latitude. White ovals, unique to the planet, exhibit similar behavior at a latitude slightly south of the Great Red Spot. The dark brown clouds, clearly openings in the tawny cloud layer, are predominantly located about 18 degrees north latitude. The detection of thermal emission is most pronounced in the planet's equatorial region, especially from the blue-gray or purple areas. Formation of clouds. Observers on Earth can see clouds created by the planet's atmosphere and capture them in images at different heights. In addition to the peak of the Great Red Spot, the white clouds signify the greatest height, showing cloud top temperatures of around 120 kelvins K. The temperature is negative 240 degrees Fahrenheit, which is equivalent to negative 150 degrees Celsius. These white frozen ammonia crystals equal to the water ice cirrus clouds found in Earth's atmosphere. The tawny clouds, widely dispersed globally, are found at lower elevations. They come from temperatures around 200 Kelvin, minus 100 degrees Fahrenheit, minus 70 degrees Celsius, suggesting they are mainly condensed ammonium hydrosulfide. Their coloration might be due to other ammonia-sulfur compounds like ammonium polysulfides. Considering the significant presence of sulfur in the universe and the absence of hydrogen sulfide in Jupiter's atmosphere above the clouds, we suggest that sulfur compounds are likely the coloring agents. Helium and hydrogen are the main elements that make up Jupiter. We think that the chemically active elements that are common will interact with hydrogen in a way that keeps everything in balance. This will let all the elements interact at a normal temperature in the area of the Jovian atmosphere that can be seen. As a result, we deduce the presence of methane, ammonia, water, and hydrogen sulfide. Spectroscopic investigations from Earth have identified all these chemicals except hydrogen sulfide. It makes sense that there isn't much hydrogen sulfide if it reacts with ammonia to form the thought-about ammonium hydrosulfide clouds. The Galileo probe found hydrogen sulfide present in lower amounts in the atmosphere. Since hydrogen sulfide can't be found above the clouds, it's likely that lightning strikes, not UV radiation from the sun, set off the chemical reactions that make the colorful sulfur compounds if they are there. We still don't fully understand the reasons behind Jupiter's colors. Nonetheless, researchers have suggested several credible options. Sulfur compounds have been proposed to explain the dark brown color of the ammonia clouds seen at lower altitudes when the measured temperature is 260 Kelvin, 8 degrees Fahrenheit, minus 13 degrees Celsius. We see these clouds through gaps in the usually widespread brown clouds. Images of Jupiter, derived from its thermal radiation at a wavelength of 5 micrometers, 0.0002 inches, exhibit brightness, indicating their elevated temperatures. Experts attribute the great red spot's hue to the presence of complex organic molecules, red phosphorus, or another sulfur compound. Laboratory investigations support these ideas. However, every case has opposing arguments. Researchers have recorded temperatures reaching 300 Kelvin, 80 degrees Fahrenheit, 27 degrees Celsius, adjacent to the apex of white plume clouds at the planet's equator, where darker areas are also present. Despite their blue-gray color, these specific hot areas show a reddish shade. These locations lack clouds, allowing clear visibility at great depths and recording high temperatures. Rayleigh's scattering of sunlight results in a blue tint, which a delicate layer of reddish material conceals. These so-called hot spots are only found near the equator. The circular dark brown clouds only show up at latitude 18 degrees north, and the Great Red Spot is the only place on Earth with the brightest red color. This suggests that there is an unusually high concentration of cloud chemistry in an atmosphere that is so dynamically active. At greater depths in the atmosphere, astronomers expect to find clouds made of ice and clouds formed from water droplets of weak ammonium hydroxide solutions. However, when the Galileo spacecraft's probe penetrated Jupiter's atmosphere on December 7, 1995, it did not detect the anticipated water clouds, despite enduring a pressure of 250 bars, 22 bars, approximately 22 times the sea level pressure on Earth, where the temperature exceeded 400 Kelvin, 260 degrees Fahrenheit, 130 degrees Celsius. The probe could not pinpoint the peaks of ammonia and ammonium hydrosulfide layers in the clouds. Regrettably for Jovian cloud physics research, the probe's entry into the atmosphere occurred over a clear, hot area, likely due to a major weather event similar to the downdrafts observed in some Earth storms. Characteristics of the atmosphere. Before the launch of the Galileo probe, astronomers relied on spectral analyses of the planet to determine the makeup, temperature, and pressure of its atmosphere. The absorption spectroscopy method uses a spectrograph's dispersive part to separate light or heat from the planet into different wavelengths, which can be thought of as colors like those in a rainbow. The resulting spectrum shows clear intervals, or lines, that correspond to the energy absorbed by the components of the planet's atmosphere. Astronomers can determine the gases in Jupiter's atmosphere by measuring the exact absorption wavelengths and comparing the results with the laboratory spectra of gases. During the 1930s, researchers deduced that methane and ammonia were present in Jupiter's atmosphere, and they recognized hydrogen for the first time in 1960. Even though molecular hydrogen is 500 times more prevalent than methane, it shows significantly weaker absorption lines because of its limited interaction with electromagnetic waves. Further research led to a growing collection of extra elements, particularly recognizing the arsenic compound arsine in 1990. If chemical equilibrium was strictly maintained in Jupiter's atmosphere, the observed abundance of compounds such as carbon monoxide or phosphine would be surprising. The detection of acetylene, ethane, and various hydrocarbons in the stratosphere goes against what was expected. Clearly, some energy sources extend beyond the molecular kinetic energy linked to local temperatures. The sun's ultraviolet rays help break down methane, leading to processes that produce acetylene and ethane. The Voyager and Galileo spacecraft observed lightning discharges within the atmospheric convective zone, adding to these phenomena. A reaction between methane and water vapor generates carbon monoxide at approximately 1,200 Kelvin, 1,700 degrees Fahrenheit, 930 degrees Celsius. The vertical mixing must be strong enough to identify this gas from outside the atmosphere. A segment of carbon monoxide, carbon dioxide, and atmospheric water comes from ice particles colliding with the planet from outer space. Galileo's probe had a mass spectrometer that recognized the atoms and molecules in the atmosphere by first charging them and then separating them with a magnetic field according to their masses. This technology had the advantage of measuring noble gases like helium and neon, which do not engage with visible and infrared light. As the probe descended through the atmosphere on its parachute, its spectrometer examined variations in abundance with altitude. This experiment successfully identified the previously undetected hydrogen sulfide, showing its presence at a lower altitude in the atmosphere than expected. The earlier noted downdraft reduced the amount of this cloud-forming gas in the upper part of the hot zone, along with ammonia and water vapor. Measuring oxygen was impossible because this element is trapped in water, and the probe did not go deep enough into the hotspot to reach the atmospheric area where this condensable vapor is evenly spread. We can compare the elemental abundances in Jupiter's atmosphere with the Sun's composition. The planet should have the same amount of each element if it formed in the same way as the Sun, by fundamental condensation from the solar nebula that is thought to have started the solar system. The Galileo probe revealed an unexpected discovery. All globally mixed elements detectable in the Jovian atmosphere exhibited the same threefold hydrogen increase compared to their Sun levels. This carries important consequences for the planet's evolution. Refer to Origin of the Jovian System later in this chapter. The spectroscopy performed from Earth shows a notable difference in the levels of various elements, particularly phosphorus, germanium, and arsenic, which were not evaluated by the probe. The amounts of gases that come from these elemental abundances change based on chemical reactions and vertical mixing that happen in Jupiter's atmosphere. The presence of deuterium on Jupiter indicates a further deviation from solar values. This dense hydrogen isotope has disappeared from the Sun because of nuclear processes at its core. As no such reactions occur on Jupiter, the ratio of deuterium to hydrogen should reflect that of the isotopes found in the interstellar gas and dust cloud that collapsed to form the solar system 4.6 billion years ago. The Big Bang is believed to have initiated the universe's expansion and produced deuterium. Therefore, a more precise measurement of Jupiter's deuterium to hydrogen ratio will aid in calibrating expansion models. There are thermal and barometric conditions. In addition to evaluating the atmosphere's makeup, the Galileo probe had instruments designed to gauge temperature and pressure as it descended into the Jovian atmosphere. The probe recorded temperatures beyond the freezing point of water, which is 273 Kelvin, 32 degrees Fahrenheit, and 0 degrees Celsius, at pressures slightly above Earth's sea level pressure, about 1 bar. This occurrence is primarily due to Jupiter's internal energy source, although some heating could also stem from the atmosphere's ability to hold onto infrared radiation, similar to the greenhouse effect on Earth. The increase in temperature above the tropopause is known as an inversion since temperature usually decreases with height. At high elevations, gases and aerosol particles absorb solar radiation, leading to the inversion. Ozone causes a similar reversal in the Earth's atmosphere. Extra likely atmospheric elements. Astronomers and several other peculiar entities expect to find monosilane in the depths of the atmosphere. Future atmospheric missions anticipate the presence of more out-of-equilibrium species in the higher areas they can reach. These species might come from chemical reactions sparked by lightning or ultraviolet radiation from the sun, or they may form near the poles where charged particles have been noted to aid in the creation of benzene. Creating complex organic molecules in Jupiter's atmosphere plays a crucial role in exploring the origins of life. The basic chemical reactions that started life on Earth may have happened in short-lived microenvironments with a chemical makeup similar to Jupiter's, but without large amounts of hydrogen and helium. As a result, Jupiter could serve as a vast natural laboratory where researchers consistently explore the initial phases of the origin of life. Evaluating the intricacies of prebiotic chemical reactions in these environments poses an intriguing challenge for any space exploration effort. On March 25, 1993, Eugene, Carolyn Shoemaker, and David Levy discovered an unidentified comet near Jupiter in photos captured at Palomar Observatory in California. Its striking appearance showcased no fewer than 12 cometary nuclei positioned like radiant pearls on a string. Over successive weeks, the nuclei dispersed increasingly, resulting in the visibility of 21 fragments. An examination of their shared orbit indicated that the original comet, orbiting the Sun, had skimmed Jupiter's atmosphere and nearly collided with it on July 8, 1992. During that time, the tidal gravitational forces exerted by the massive planet broke the nucleus into many pieces, which were later captured by Jupiter's gravity and placed into a prolonged 2-year orbit around the planet. Astronomers determined that the revised orbit would return the fragments to Jupiter in July of 1994. The shards of Shoemaker-Levy 9 collided with Jupiter's atmosphere at a speed of 216,000 kilometers, 134,000 miles per hour, commencing on July 16, 1994. All of them were struck by the unseen edge of Jupiter beyond its horizon, as seen from Earth. The planet's 10-hour rotation rapidly exposed each impact location. Separated by an average of 7 to 8 hours, each component descended into the Jovian atmosphere, creating prominent scars near latitude 44 degrees south. Astronomers assigned the individual components capital letters sequentially according to their arrival. Fragment G was likely the largest and heaviest, with an estimated diameter of 3 to 4 kilometers, 1.9 to 2.5 miles. It formed a dark, multi-ringed mark that was 2 times the circumference of Earth. The collision unleashed energy comparable to several trillion tons of TNT, exceeding the output of the entire global nuclear arsenal by hundreds of times. Each collision quickly transformed into a large sphere of hot gas that radiated a gentle light in infrared images of Jupiter as it expanded over several days within the atmosphere. The large dark brown spots, considered tiny organic particles from comets, remained visible for several weeks. The powerful winds of Jupiter slowly reduced its prominence, creating a new. Scientists used spectroscopic techniques to find out that the impacts made or brought in different molecules, like water, hydrogen cyanide, and carbon monoxide, which are all found on Jupiter, but in much smaller amounts. The excess carbon monoxide and hydrogen cyanide lingered in the upper atmosphere for years after the event. In addition to its intrinsic importance, the impact of a comet on Jupiter led to extensive studies regarding the effects of cometary collisions on Earth. A dark spot that looked like fragments of Comet Shoemaker-Levy 9 appeared close to Jupiter's southern pole in 2009. The observation of one impact site led scientists to determine that the hitting entity was a single body, a comet or an asteroid, rather than multiple fragments. Researchers identified Jupiter as the first planet to emit radiation at radio wavelengths in 1955. Scientists recorded noise bursts of radiation with a frequency of 22 megahertz, which is equal to a wavelength of 13.6 meters or 44.06 feet. Occasionally, the maximum intensities of these bursts rendered Jupiter the most luminous object in the sky at this wavelength, surpassed only by the Sun during its peak activity. The emissions of radio interference from 3 distinct regions served as the preliminary evidence of a Jovian magnetic field. Subsequent measurements at shorter wavelengths, specifically in the decimeter range, revealed that Jupiter also emits continuous radio waves. It has become standard to refer to these 2 types of emissions by their specific wavelengths: decameter radiation and decimeter radiation. The non-thermal part of the continuous decimeter radiation is due to synchrotron emission. This occurrence is due to electrons moving at incredibly high speeds within Jupiter's magnetic field in a donut-shaped area around the planet. This occurrence closely mirrors the Van Allen belts found on Earth. The Cassini orbiter identified the peak emission at 13,800 megahertz, the operational frequency of the spacecraft's radar instrument, from Earth at a distance of 2 planetary radii from the planet's core. The emission intensity and its polarization plane, which is the plane where radio emission oscillations predominantly occur, vary with the same periodicity. Both phenomena become clear when the axis of the planet's magnetic field is tilted about 10 degrees about the rotational axis. System 3 recognizes the rotation period as the length of these fluctuations. Random radio emissions at decameter wavelengths from Earth have been studied by researchers in the frequency range of 3.5 MHz to 39.5 MHz. The radio wave experiment on the Voyager spacecraft was able to pick up emissions from Jupiter as low as 60 kHz, which is equal to a wavelength of 5 kilometers, 3 miles. This was possible because Earth's ionosphere blocks lower frequencies from reaching the surface. The strength of the radio signal and the occurrence of noise storms show a notable relationship over time, which helped in the early detection of 3 sources, or emitting locations. We initially determined the rotational period of System 3 by observing the regularity of these sources. The orbital position of Jupiter's moon, Io, significantly impacts the decameter noise storms. One source says that things are much more likely to happen when Io is at a right angle to the lineup of Earth, Jupiter, and Io. This is called superior geocentric conjunction, and it's different from other positions. Unlike non-thermal decimetric radiation, the noise sources appear to be regions in the direct line of sight to the planet's visible disk. The emissions are linked to a certain area by magnetic field lines, also called flux tubes, that are connected to Io. This is the best explanation for how Io's orbital motion affects noise storms. Electrons moving in a spiral around magnetic field lines might produce the radiation we observe. The Voyager and Galileo spacecraft foresee and identify interactions between these electrons and the Jovian ionosphere. Earth can sense the footprint of Io's flux tube on Jupiter's upper atmosphere, appearing as a bright spot associated with Jupiter's polar auroras, the magnetic field and magnetosphere. Non-thermal radio emissions occur naturally due to trapped charged particles interacting with Jupiter's magnetic field and ionosphere. The Pioneer and Voyager spacecraft's direct examination of Jupiter's surroundings led to a highly accurate characterization of the planet's magnetic field and magnetosphere through the analysis of these observations. The hydromagnetic dynamo in Jupiter's electrically conductive outer layers generates the planet's dipolar fundamental magnetic field. The magnetic moment is 19,000 times superior to Earth's, resulting in an equatorial field strength of 4.3 Gauss, in contrast to 0.3 Gauss at Earth's surface, On Jupiter, the magnetic dipole axis is shifted by 10 degrees from the planet's rotational axis, which is 71,500 kilometers, 44,400 miles, away. A compass on Earth pointing toward Jupiter would show the south, as Jupiter's magnetic field is reversed compared to Earth's. The magnetic field dominates the region around Jupiter, creating a stretched teardrop shape. The rounded side of the teardrop orients towards the Sun, while the Jovian magnetic field deflects the solar wind, creating a bow shark approximately 3 million kilometers from the planet. Opposite the Sun, a vast magnetotail extends to the orbit of Saturn, almost 650 million kilometers away, nearly equivalent to Jupiter's distance from the Sun. These dimensions make Jupiter's magnetosphere the largest lasting structure in the solar system, exceeding the Sun's diameter of 1.4 million kilometers, 870,000 miles. Io, the Moon, generates the most extraordinary activity in this vast region, and the earlier section explores its influence on decametric radiation. An electric current of approximately 5 million amperes flows through the magnetic flux tube of Jupiter and Io. This satellite creates a donut-shaped cloud of ions, or plasma, surrounding its path in orbit. The energy that supports this immense magnetosphere comes from the rotation of the planet, which must therefore be slowing down at an almost undetectable rate. Charged particles, like electrons, are driven to move across the planet by the magnetic field lines, traveling at a speed that matches the planet's rotation cycle. As a result, terrestrial radio astronomers could determine System 3's rotation period well before any spacecraft made the discovery. It takes Io 42.5 hours to make one full orbit around Jupiter, but the magnetic field of Jupiter pulls in charged particles, which makes the ions it sends out during its orbit oscillate with a System 3 period of about 10 hours. As a result, the plasma wake of Io comes before the Moon's path around Jupiter. The auroras. Just as charged particles are trapped within the Van Allen belts, creating stunning auroras on Earth when colliding with the upper atmosphere near the magnetic poles, they produce auroras on Jupiter. The Voyager and Galileo spacecraft cameras effectively recorded images of ultraviolet auroral arcs on the night side of Jupiter. The Hubble Space Telescope captured images of far ultraviolet auroras on the planet's day side. Additionally, ground-based studies have observed infrared emissions from hydrogen ions at both poles and have taken images of the related polar auroras. Protons, also known as hydrogen ions, represented as H+, from the magnetosphere spiral into the planet's ionosphere along magnetic field lines. When they collide with the predominantly molecular hydrogen-rich atmosphere, this movement generates excited H+ ions. The emission that follows makes auroras that can be seen from Earth at wavelengths, where methane in Jupiter's atmosphere has strong absorption bands. This lowers the background light from sunlight reflection. Researchers are still looking into how ultraviolet and infrared auroras affect each other, how Io's flux tube interacts with Jupiter's ionosphere, and how ions from Io's torus might affect Jupiter's atmosphere. The interior. Jupiter's atmosphere constitutes only a tiny fraction of the planet, much like the skin of an apple compared to its interior. Since directly observing anything below the thin outer layer is impossible, we deduce the makeup of Jupiter's interior based on the available evidence. Astronomers can determine the shape of the planet, its deviation from a perfect sphere, and its difference from an ellipsoidal shape by using observable quantities such as air temperature and pressure, mass, radius, shape, rotational velocity, thermal equilibrium, and disturbances in satellite orbits and spacecraft trajectories. Theoretical models for the internal distribution of materials can also predict the following amounts. Next, we can assess these models by comparing them with the observations. The biggest problem with making a model that really shows how Jupiter's interior works is that we need a lot of lab data about how hydrogen and helium behave. at very high temperatures and pressures close to the planet's center. Estimates suggest the center temperature is roughly 25,000 Kelvin, 44,500 degrees Fahrenheit, 24,700 degrees Celsius, signifying an internal heat source that allows Jupiter to emit nearly double the energy it absorbs from the Sun. The core pressure ranges from 50 to 100 million atmospheres, equivalent to around 50 to 100 megabars. We expect hydrogen to appear metallic when subjected to such extreme pressures. Despite the difficulties in figuring out the properties of matter under these extreme conditions, the precision of the models has steadily improved. One of these investigations' most significant early discoveries was that Jupiter cannot consist solely of hydrogen, which would require a considerably larger size to align with its mass. On the other hand, hydrogen should be the main element, making up at least 70% of the planet's mass, regardless of whether it is in a gaseous, liquid, or solid form. The Galileo probe detected a helium mass fraction of 24% in Jupiter's upper atmosphere, in contrast to the 28% anticipated if the atmosphere mirrored the composition of the primordial solar nebula. Astronomers have found that some helium dissolved in the fluid hydrogen inside the planet's interior came out of solution and sank toward the planet's core, reducing this gas in the atmosphere. This is because the planet should inherently have that original makeup. Clearly, the world has absorbed a significant amount of neon. This rainfall continues as the world keeps getting colder. Modern models agree that the shift from molecular to metallic hydrogen happens at approximately 1/4 of the way to Jupiter's core. This change does not occur between a liquid and a solid, but between two fluids with different electrical properties. The metallic state frees electrons from their nuclei, granting hydrogen metallic conductivity. No solid surface is present in any of these models. However, most, though not all, include a dense core with a radius ranging from 0.03 to 1/10 times that of Jupiter, 330 thousandths to 1.1 times the radius of Earth. We need to thoroughly determine the source of internal heat. As of now, the most popular theory is a mix of the slow release of primordial heat from the planet's formation and the release of thermal energy from the condensation of helium droplets deep inside the planet, similar to what happens on Saturn. The lower helium in Jupiter's atmosphere than that of the Sun supports this conclusion. The first step is the cooling phase of the original collapse, which transformed potential energy into thermal energy when the planet gathered its gas, see origin of the Jovian System. The first celestial bodies in the solar system observed through a telescope by Galileo in 1610 were the 4 brightest moons of Jupiter, now known as the Galilean satellites. Edward Emerson Barnard visually discovered the 5th known Jovian moon, Amalthea, in 1892. Photographs or computerized images captured by Earth-based telescopes or the cameras on the Voyager spacecraft have identified all other known satellites. In 1979, Voyager photos unveiled Jupiter's multifaceted ring system. The paths of the 8 inner moons show very little variation and tilt. In other words, their orbits are mostly round and in line with the planet's equator. These moons are referred to as regular. The orbits of the many moons found beyond Callisto show much higher inclinations and eccentricities, classifying them as irregular. The 2 innermost moons, Metis and Adrastea, are closely associated with Jupiter's ring system, providing fine particles and functioning as gravitational shepherds. Amalthea and Thebe also play a role in the ring system by creating fine, delicate rings located further from the planet. There may be other unknown minor moons that exist near Jupiter. We may yet discover additional distant irregular moons beyond the ones we currently know, the Galilean moons. Galileo proposed the name Medicean stars for the 4 Jovian moons he discovered in 1610. Honoring his patron, Cosimo II de' Medici. However, they later came to be referred to as the Galilean satellites in acknowledgement of their discoverer. Galileo viewed their existence as crucial proof backing the Copernican heliocentric model, in which the planets orbit the Sun. The orbits of T-Sun around Jupiter violated the Ptolemaic system, which required that all celestial bodies revolve around Earth. In Greek mythology, the satellites Io, Europa, Ganymede, and Callisto are closely connected and listed in order of their increasing distance from the planet. Simon Marius, a German astronomer and a contemporary rival of Galileo, certainly made an independent discovery of the satellites and assigned their names. The choice of the name Io shows significant importance. Io, the wanderer, Greek ion, going, has an indirect influence on Jupiter's ionosphere. Observations from Earth had determined the approximate sizes and spectroscopic properties of the Galilean moons, but the Voyager missions confirmed these four entities as unique worlds. The Galileo mission produced a wealth of additional information. Before Voyager, we knew that Callisto, Ganymede, Europa, and Io are all about the same size or bigger than Mercury, that their surfaces are covered in water ice, and that Io's orbit is surrounded by a ring-like structure of atoms and ions that include sodium, potassium, and sulfur. We also knew that the average densities of the two inner Galilean moons are much higher than those of the two outer moons. The density gradient from Io to Callisto is similar to that of the solar system and comes from the same source. The density values indicate that Io and Europa possess a stony composition similar to the Moon, while Ganymede and Callisto probably consist of a significantly less dense material, likely water ice. Can you express the numbers in written form? Impact craters dominate the cold surface of this moon, preventing the formation of flat plains similar to the dark Rhea seen on the Moon. In other terms, there are no areas on Callisto where the appearance of material from below the surface, due to later internal activity, has removed any signs of early impacts. This record was formed by the collision of debris, including comet nuclei and asteroidal material, primarily during the first 500 million years after the solar system's birth, similar to how craters are produced on the Moon. The surface looks the same, which matches the absence of a distinct interior. Unlike the other three Galilean moons, Callisto did not undergo global heating caused by tidal forces, nor did it experience melting. Deposits of fine black material, similar to a mixture of clay minerals, cover craters smaller than 10 kilometers, 6 miles, as the Galileo spacecraft shows. Alongside the abundant water ice, the surface features solid carbon dioxide, and a very thin atmosphere of carbon dioxide slowly fades away into the void of space. Other trace surface components consist of solar ultraviolet energy causes photochemical reactions in ice that produce hydrogen peroxide. It is presumed that sulfur and its components originate from Io. Collisions of comets might have brought organic molecules into existence. The magnetic field of Jupiter produces a subtle magnetic influence on Callisto, indicating the possible presence of a liquid water layer hidden beneath its icy surface. Unlike Callisto, Ganymede, also a frozen satellite, shows clearly marked dark and light terrain areas. This distinction is akin to the surface of the Moon. Nonetheless, the question of which landscape came first, dark or light, is essentially inverted. In contrast to the Moon, the darker regions on Ganymede are older, showcasing the greatest concentration of craters. The highlighted regions suggest a more contemporary period. Ray systems typically surround the complex layout of parallel and intersecting ridges and grooves, along with remarkably bright impact craters. Dynamic crustal movement and surface renewal provide clear evidence of internal differentiation. Unlike Callisto, Ganymede has a core rich in iron and a strong, permanent magnetic field capable of creating its magnetosphere and auroras. There is less clay-like dust on Ganymede's icy surface than on Callisto, but the same amount of solid carbon dioxide, hydrogen peroxide, and sulfur compounds are present. There are also signs of molecular oxygen and ozone being trapped in the ice. While the infrared spectra of Ganymede and Callisto show evidence of ice coverage, Europa's surface is notably different. Europa has a small number of impact craters, with a density per unit area similar to Earth's continental areas, indicating that its surface is quite young. Some specialists think the surface is quite recent, indicating that significant resurfacing is ongoing on the satellite. This resurfacing involves water outflow from the interior, creating an ocean that freezes instantly. An iron-rich core is thought to be inside the differentiated interior, surrounded by a silicate mantle and topped by an ice crust that is about 150 kilometers thick. This moon possesses both induced and intrinsic magnetic fields. Researchers have discovered salt deposits in somewhat mottled regions on the lunar surface, indicating the evaporation of water from an underground reservoir. The frozen surface of Europa features a captivating mix of dark and bright stripes, along with curvilinear ridges and grooves that cross each other. Spatter cones found in specific channels suggest the occurrence of subsurface fluid explosions. The landscape is predominantly level, with ridge heights peaking at just a few hundred meters at most. Europa has the smoothest surface of any solid celestial body studied in the solar system. Researchers have found signs of sulfur, sulfur compounds, hydrogen peroxide, and organic molecules on the surface. The main unanswered question is if a global ocean of liquid water beneath Europa's ice is warmed by the release of tidal energy within Europa's interior. The possibility of such an ocean arose from Voyager data, and detailed photographs from Galileo showed fluid movement on the surface. Additionally, explaining Europa's induced magnetic field requires the existence of a fluid medium that can conduct electricity. This shows that there is a layer of saline liquid water located beneath the surface ice. If this ocean and its necessary heat source are present, we should acknowledge the likely presence of some microbial life forms. When viewed through a telescope from Earth, Io shows a reddish-orange color, whereas the other moons present a neutral shade. Io's infrared spectrum shows no signs of the absorption characteristics of water ice. Scientists expected that Io's surface would be distinct from Jupiter's other moons, but the Voyager images revealed a more strange landscape. Fissures from volcanic activity instead of craters from impacts mark the surface of Io. In 1979, the two Voyager spacecraft detected 9 erupting volcanoes. But Galileo's closer observations indicated that as many as 300 volcanic vents might be active simultaneously. The silicate lava ejected from the vents is exceedingly hot, approximately 1,900 Kelvin, 3,000 degrees Fahrenheit, and 1,630 degrees Celsius, akin to primordial lavas on early Earth. This remarkable phenomenon makes Io the most tectonically active body in the solar system. This volcanic activity completely and consistently refreshes the satellite's surface over several thousand years. Various allotropes of sulfur are probably accountable for the black, orange, and red areas of the moon's surface, while solid sulfur dioxide is likely the main element of the white regions. Voyager's infrared spectrometer found sulfur dioxide as a gas close to an active volcanic plume, but studies done in space and on the ground using ultraviolet and infrared light showed it to be a solid. The names confirm where the sulfur and oxygen ions seen in Jupiter's magnetosphere come from, showing that Io's particle torus is made by its volcanic activity. The force behind this volcanic activity needs a clear explanation, since nuclear heating is insufficient for a body as small as Io. The most popular theory is based on the discovery that Io's orbit is thrown off by its resonances with the other Galilean moons. This makes Io's orbit longer than if Jupiter alone had affected it. The gravitational interactions among Io, other satellites, and Jupiter create tides that release enough energy to account for the observed volcanism. The inside consists of a thick, iron-heavy center that probably produces a magnetic field. The interactions of Io with Jupiter's magnetosphere and ionosphere are so complex that it has been difficult to differentiate the satellite's own field from the fields produced by Amalthea, a small, oddly shaped moon of Jupiter, named after a figure from Greek mythology associated with the young Jupiter, was the only other moon close enough to the Voyager spacecraft's path for surface features to be visible. Amalthea orbits Jupiter every 11 hours and 57 minutes, 0.498 Earth days, at a distance of 181,000 kilometers, 112,500 miles, in a roughly circular trajectory aligned within half a degree of Jupiter's equatorial plane. Images sent by the Voyager 1 and 2 spacecraft in 1979 and confirmed by the Galileo orbiter in the late 1990s show that Amalthea is a rough, rocky object that is 260 kilometers long, 136 kilometers wide, and 134 kilometers high. Like the Moon, which always shows the same side as Earth, Amalthea spins in sync with its path around Jupiter, keeping a steady alignment with the planet. Amalthea's long axis always points in the direction of Jupiter. By evaluating Amalthea's gravitational influence on the Galileo spacecraft, scientists determined that the Moon has a remarkably low density of 0.9 grams per cubic centimeter, enabling it to remain buoyant in water. Amalthea is filled with holes, probably because of several impacts breaking apart its granite core. We have also observed low densities for specific inner moons of Saturn, which we attribute to this factor. Amalthea's surface is dark and reddish, marked by impact craters. The leading hemisphere, facing the direction of motion, is about 30% brighter than the trailing hemisphere, possibly because of impacts from small meteoroids that have come into the Jovian System. The nearby volcanically active moon Io constantly releases sulfur and compound particles, likely explaining its reddish color. The most extensive impact crater on Amalthea is Pan, measuring approximately 90 kilometers in diameter. The Galileo orbiter delivered fresh images of Amalthea and noted the consequences of impacts on Thebes and Metis. Like Amalthea, these two moons are tidally locked, always showing the same side to Jupiter, and exhibit a brightness increase of about 30% on their leading hemispheres. Two distinct orbital groups comprised 8 outer moons identified before the 21st century. The more distant group, Ananke, Carme, Pasiphae, and Sinope, shows retrograde orbits around Jupiter. The inner group, consisting of Leda, Himalaya, Lysithea, and Ilara, shows prograde orbits. For these moons, retrograde motion occurs in the direction opposite Jupiter's rotation and its orbit around the Sun, but counterclockwise when viewed from above Jupiter's north pole. On the other hand, prograde motion aligns with these movements. In 1999, astronomers systematically searched for new Jovian satellites, employing highly sensitive electronic detectors capable of identifying fainter and subsequently smaller objects. After finding many more outer moons in the following years, they realized that dividing them into two families was too simplistic. More than 100 tiny debris, classified into various categories according to their orbits, are likely orbiting Jupiter. Every group appears to have originated from a single entity Jupiter captured and broke apart. The captures probably took place close to Jupiter's formation when a nebula surrounded the planet, slowing down anything that came into it. The Trojan asteroids might have a connection to these small moons. In 1974, as the Pioneer 10 spacecraft got closer to Jupiter, it noticed a big drop in the number of charged particles. This happened about 125,000 kilometers, 78,000 miles, from Jupiter in the orbit of its innermost moon Metis. This suggested the possible existence of a moon or a ring of material surrounding the planet at this distance. The initial Voyager spacecraft confirmed the presence of a ring in 1979 upon traversing the planet's equatorial plane. In contrast, the subsequent spacecraft captured further images, including a sequence in the planet's shadow, directed towards the Sun and the ring. The ring looked much more luminous from this perspective. Most of the ring particles are more efficient at scattering light in the forward direction compared to the reverse direction toward Earth. As a result, it was not surprising that ground-based observations failed to identify the ring before the discoveries made by Voyager. The forward scatter suggests that most particles are small, within the micrometer size range, similar to the tiny specks of dust seen in a sunbeam on Earth, or the minute particles on a car windshield, which display a comparable optical effect. Images obtained by the Galileo spacecraft between 1996 and 1997 showcase the complex arrangement of the ring. There exists an outer gossamer ring, imperceptible beyond the orbital radius of the satellite Thebe, 222,000 kilometers, and an inner gossamer ring, confined by the orbit of Amalthea, 181,000 kilometers. The main ring is about 30 kilometers, 18 miles, wide, and goes from the orbits of Adrastea, 119,000 kilometers, 85,000 miles, and Metis, 118 kilometers, 000 kilometers, 72,953.35 miles to an inner boundary at 123,000 kilometers, 72,943.28 miles. Furthermore, a toroidal halo of particles stretches from the primary ring inward to 92,000 kilometers. The presence of micrometer-sized particles in the ring requires a source, and the relationship between the ring limits and the 4 moons clarifies the source's origin. The ring particles are made when micrometeoroids, cometary debris, and maybe even material from Io's volcanoes crash into these moons and smaller bodies in the main ring. As the planet turns, the electrically charged particles react to the fluctuations of the Jovian magnetic field. The Jovian System. Explaining the origins of the solar system involves shedding light on the formation of Jupiter and its moons. Modern theories endorse the gradual formation of the Sun and planets from a massive cloud of gas and dust marked by gravitational instabilities that triggered the cloud's collapse. Traditional theories suggest that Jupiter formed from the condensation of the early solar nebula due to its significant hydrogen content and enormous mass. This concept implies that Jupiter should have the same elemental ratios as the Sun. Recent research suggests that the proportions of Jupiter's components differ from the typical solar standards. Modern theories regarding the formation of Jupiter suggest that a solid core, roughly 10 times the mass of Earth, was first created through the accumulation of frozen planetesimals. The core would have produced its own atmosphere, as the planetesimals released gases throughout the accretion process. As the core's mass grew, it would have become able to pull gases from the nearby solar nebula. This created the huge envelope of hydrogen and helium that makes up Jupiter's atmosphere and fluid mantle. The accumulating envelope would have engaged with the outgassed atmosphere in the core. In this way, the current enrichment of the main heavy elements in this envelope compared to solar values shows that these elements are gathering in the core. The mass spectrometer on the Galileo probe indicated an enrichment of nearly 3 times these heavy elements. For this enrichment to include volatile gases like argon and molecular nitrogen, the ice planetesimals must have come from temperatures of 30 Kelvin or lower. This is equal to negative 402 degrees Fahrenheit or negative 294 degrees Celsius. The mystery of this event lingers, and understanding it could shed light on the existence of significant planets close to their stars in different planetary systems. Many think that the origin of Jupiter's 8 inner moons is similar to that of the planet. Just as the original solar nebula broke apart into gathering planetesimals that created the planets and a central mass that turned into the Sun, the ASU negation of material within a protoplanetary cloud at Jupiter's orbit eventually led to the creation of the planet and its inner moons. The comparison goes even deeper. The high temperature during the formation of Jupiter appeared to prevent the condensation of volatile compounds near the closest moons. As a result, Ganymede and Callisto, the most distant of the 8 inner moons, serve as prime examples of the volatile-rich outer bodies in this system. The creation of many tiny outer moons, known for their highly varied orbits and angles, is unique. They are part of the irregular satellites within the solar system and are likely captured objects. Their ultimate origin, on the other hand, stays unclear. The parent bodies of these moons might have come from Jupiter's outer nebula, strayed, and then been retrieved. On the other hand, they could have developed independently within the solar nebula and subsequently been recaptured. In both scenarios, the capture process resulted in the breakdown of the parent bodies, giving rise to the debris we now identify as the outer irregular moons. Ongoing studies of these objects and their possible connections to the Trojan asteroids could clarify their beginnings. Can you express the numbers in written form? Unaided eyes may readily observe Saturn in the night sky as a stable point of light, and even a modest telescope can unveil the planet's remarkable rings, making it perhaps the most beautiful object in the solar system. Saturn originates from the Greek god Cronus, a Titan who is the progenitor of Zeus, and the Roman god Jupiter. Ancient astronomers noted that Saturn was the planet with the slowest movement and the greatest distance from the Sun. Saturn, at a distance of 9.5 times that of Earth from the Sun, takes about 30 Earth years to complete one solar revolution. In 1610, the Italian astronomer Galileo became the first to observe Saturn through a telescope. Even though he noticed something unusual about Saturn's look, the low resolution of his instrument prevented him from understanding the real characteristics of the planet's rings. Saturn is the second largest planet in the solar system by mass and size, and it ranks 6th in distance from the Sun. It makes up more than 60% of Jupiter's volume, but has about 1/3 of its mass, showing the solar system's lowest average density, around 70% of water, of any known object. Saturn would, in theory, float in an ocean that is large enough. Hydrogen is the most abundant element in the overall chemical composition of Saturn and Jupiter, similar to that of stars. Like Jupiter, Saturn's core's immense pressure maintains hydrogen in a fluid metallic state. However, Saturn's makeup and development path differ from its bigger counterparts. Like the other gas giants, such as Jupiter, Uranus, and Neptune, Saturn has extensive systems of moons and rings that could provide valuable information regarding its origin, evolution, and that of the solar system. Titan stands out among other moons due to its dense atmosphere, which is thicker than any terrestrial planet except for Venus. A thorough understanding of Saturn and many other planets comes from deep space probes. 4 spacecraft have explored the Saturnian system. Pioneer 11 in 1979, Voyagers 1 and 2 in the subsequent 2 years, and Cassini-Huygens commencing in 2004 after an almost 25-year interval. The first 3 missions were short flybys, while Cassini entered orbit around Saturn for a long duration of research, and its Huygens probe descended through Titan's atmosphere and landed on its surface, marking the first time a spacecraft landed on a moon other than Earth's. Saturn revolves around the Sun at an average distance of 887 million miles. Its distance from Earth is consistently no less than approximately 1.2 billion kilometers, 746 million miles, and its phase angle, the angle formed with the Sun and Earth, never surpasses approximately 6 degrees. Saturn often appears nearly fully illuminated due to its closeness to Earth, a limitation that deep space spacecraft have eventually overcome. Like Jupiter and most other planets, Saturn has a steady orbit. In particular, its path around the Sun is prograde, in line with the Sun's rotation, and shows little eccentricity, departure from a perfect circle, and inclination compared to the ecliptic plane of Earth's orbit. In contrast to Jupiter, Saturn's rotational axis is tilted by 26.7 degrees relative to its orbital plane. The axial tilt of Saturn creates seasons akin to those on Earth. Nevertheless, each season lasts more than 7 years. Observers on Earth see Saturn's rings, which are aligned with its equator, at angles of inclination ranging from 0 degrees, edge-on, to nearly 30 degrees. The viewpoint of Saturn's rings transforms every 30 years. Observers on Earth can see the bright northern side of the rings for about 15 years, and then they can observe the bright southern side for the next 15 years. The rings are not noticeable during the brief moments when Earth crosses the ring plane. Saturn does not have a consistent rotation period. The movements of clouds in its extensive upper atmosphere exhibit diverse durations, ranging from approximately 10 hours and 10 minutes at the equator to about 30 minutes longer at latitudes over 40 degrees with significant oscillation. Researchers have established the rotation period of Saturn's inner core by analyzing its magnetic field, which is believed to originate from the planet's metallic hydrogen outer core. Measuring the rotation of the field directly is quite difficult because of its impressive symmetry around the axis of rotation. During the Voyager encounters, radio emissions from Saturn, which were linked to small changes in the magnetic field, lasted for 10 hours and 39 minutes and 4 seconds. This time was used to figure out how long the magnetic field rotated. 25 years later, however, certain Cassini data suggested that the field was revolving, extending a period of 6 to 7 minutes. Differences in the measurements of rotational periods could be caused. We have used the time differences between the rotation periods of Saturn's clouds and its interior to estimate wind speeds. Other radio bursts, lasting approximately 10 hours and 10 minutes, emanate from lightning within Saturn's atmosphere. Traditionally, we ascertain the radius and gravity of the 4 gas giants at 1 bar of atmospheric pressure, as their outer layers do not possess a solid surface. The equatorial diameter of Saturn is 120,536 kilometers, 74,898 miles. In contrast, its polar diameter measures merely 108,728 kilometers, 67,560 miles, or 10% smaller, rendering Saturn the most oblate planet in the solar system. The shape is clearly visible, even through a simple telescope. Even though Saturn spins slightly slower than Jupiter, it shows more flattening because its rotation pushes back against a larger share of the planet's gravity at the equator. The planet's equatorial gravity, measuring 896 centimeters, 29.4 feet, per second squared, constitutes merely 74% of its polar gravity. Saturn has a mass that is 95 times greater than Earth's, while its volume is 766 times larger. The average density is 0.69 grams per cubic centimeter, or 0.4 ounces per cubic inch, approximately 12% of Earth's density. The equatorial escape velocity of Saturn, which includes individual atoms and molecules, is approximately 36 kilometers per second, 80,000 miles per hour, at the 1 bar level, compared to Earth's 11.2 kilometers per second, 25,000 miles per hour. This high value indicates that Saturn has experienced no significant atmospheric loss since its formation. The atmosphere. From Earth's viewpoint, Saturn is mainly misty yellow-brown. Telescopes and spacecraft imagery reveal a layered structure of clouds on the surface. Similar to other gas giants, the atmospheric circulation of Saturn is mainly defined by zonal flow, which moves predominantly in an east-west direction. This appears as a sequence of lighter and darker cloud bands similar to those found on Jupiter, yet Saturn's bands display more subtle hues and are wider around the equator. The characteristics of the cloud tops show very little contrast, allowing the Voyager flybys to support a thorough study of Saturn's atmospheric circulation. When described by the rotation of its magnetic field, almost all of Saturn's atmospheric currents, or winds, move eastward, aligned with the direction of rotation. The eastward flows are significantly more noticeable than Cassini's diminished magnetic rotation rate. In latitudes around 20 degrees, the equatorial zone demonstrates a notably vigorous eastward current, reaching a peak velocity near 500 meters per second, 1,800 kilometers, 1,100 miles per hour. This characteristic is similar to one found on Jupiter, yet it extends across double the latitude and functions at quadruple the speed. In contrast, the most intense winds on Earth are observed in tropical cyclones, where, in extreme cases, sustained speeds can exceed 67 meters per second, 240 kilometers per hour. The zonal flows show remarkable symmetry around Saturn's equator, with each flow at a particular northern latitude generally having a matching flow at a similar southern latitude. At 46 degrees north and south and approximately 60 degrees north and south, we find robust eastward currents with relative velocities surpassing 100 meters per second, 360 kilometers, 225 miles per hour. We observe nearly consistent westward currents at 40, 55, and 70 degrees north and south within the magnetic field's reference frame. Following the Voyager visits, improvements in Earth-based instruments enabled distant observations of Saturn's clouds. The studies over multiple years typically match the detailed Voyager measurements of zonal fluxes, confirming their consistency over time. High-resolution measurements of Saturn's atmosphere showed a notable decline in the speed of the equatorial jet between 1996 and 2002. However, an examination of the Cassini orbiter data shows that any speed decrease is confined to the outer layers of the atmosphere. The overall symmetry from north to south indicates a potential connection with the zonal circulation happening inside. Theoretical modeling of a deep convecting fluid planet like Saturn shows that differential rotation happens along cylinders that are lined up with the planet's main axis of rotation. So Saturn's atmosphere could be made up of a series of coaxial cylinders lined up north to south, with each spinning at a different speed. This would create the zonal jets seen on the surface. A notable break in Saturn, like the core, could disturb the flow of the cylinders. The atmosphere of Saturn exhibits many smaller-scale features akin to those seen on Jupiter, such as red, brown, and white patches, bands, eddies, and vortices that change quickly. Furthermore, Saturn's atmosphere, although displaying a much more muted appearance, is not as dynamic as Jupiter's on a smaller scale. From September to November 1990, a remarkable anomaly transpired as a substantial pale-hued storm system emerged near the equator, extended to about 20,000 kilometers, 12,400 miles in size, and ultimately encircled the equator before dissipating. Observers have noted storms comparable in magnitude to the Great White Spot, analogous to Jupiter's Great Red Spot, occurring approximately every 30 years since the late 19th century. This approximates Saturn's orbital period of 29.4 years, indicating that these storms are seasonal occurrences. Initial data examination from the Voyager spacecraft showed that the planet's atmosphere consists of 91% molecular hydrogen by mass, establishing it as the most hydrogen-rich environment in the solar system. Indirect observations suggest that helium, which makes up an extra 6%, is not as common as hydrogen compared to a gas with the same composition as our Sun. If hydrogen, helium, and other elements were to exist in the same proportions as found in the Sun's atmosphere, then Saturn's atmosphere would consist of approximately 71% hydrogen and 28% helium by mass. Some theories say that helium may have split off from Saturn's outer layers. However, new research suggests that the Voyager study may have overestimated the amount of helium in Saturn's atmosphere, making it more like the value on Earth. Other significant chemicals detected in Saturn's atmosphere include methane and ammonia, which are 2 to 5 times more prevalent in hydrogen than a solar composition gas. Hydrogen sulfide and water, considered essential elements of the deeper atmosphere, remain undiscovered. Minor compounds identified spectroscopically from Earth include phosphine, carbon monoxide, and germane. Such molecules would stay hidden in a hydrogen-rich atmosphere at a chemical balance. These might be the results of reactions that are not in equilibrium, occurring at high pressure and temperature in the deep atmosphere of Saturn beneath the visible clouds. We observe a variety of non-equilibrium hydrocarbons in the stratosphere of Saturn, including acetylene, ethane, propane, and methylacetylene. Photochemical reactions can produce everything that has been previously mentioned. Astronomers on Earth have examined the bending of starlight and radio waves from spacecraft moving through Saturn's atmosphere to gather information on the atmospheric temperature at depths that correspond to pressures ranging from 1/1,000,000th of a bar to 1.3 bars. Small chemical molecules come together in the atmosphere rich in hydrogen, creating Saturn's visible cloud layer. Photographic reactions create particles floating in the air at pressures between 20 and 70 millibars. On the other hand, clouds form at pressures higher than 400 millibars. Solid ammonia crystals are believed to constitute the uppermost cloud layer. We expect that the foundation of the ammonia cloud layer will be situated at a depth of about 1.7 bars, where the ammonia crystals break down into hydrogen gas and suddenly disappear. We mostly understand the deeper layers of clouds by using chemical models that copy how molecules behave in a gas that is similar to the Sun's atmosphere, using Saturn's temperature-pressure profile as a guide. Between 4 and 7 bars, you can find the bottom of deeper cloud layers made up of ammonium hydrosulfide crystals, and between 10 and 9 bars, you can find water ice crystals with ammonia droplets in water. Although all the clouds mentioned earlier would appear colorless in their pure state, the actual clouds of Saturn display a variety of yellow, brown, and red shades. Chemical impurities, particularly those containing phosphorus, appear to produce these colors. Even though the lowest layers of Saturn's atmosphere are under a lot of pressure, the lowest temperature of 82 Kelvin is still too low for molecular hydrogen to be in equilibrium as both a gas and a liquid at the same time. As a result, there is no distinct boundary between the upper atmosphere, where hydrogen mainly exists in gaseous form, and the lower atmosphere, which appears more like a liquid. Unlike Earth's tropopause, Saturn's troposphere does not end at a defined boundary, but appears to extend for tens of thousands of kilometers below the visible clouds, reaching temperatures in the thousands of kelvins and pressures that surpass 1,000,000 bars. The magnetic field and magnetosphere. Like a fundamental dipole or bar magnet, Saturn's magnetic field positions its north-south axis within 1 degree of its rotational axis, with the center of the magnetic dipole close to the planet's core. The magnetic polarity of Saturn's field, similar to that of Jupiter, is reversed about Earth's current field. In particular, the field lines originate from Saturn's northern hemisphere and return to the southern hemisphere. Furthermore, Saturn's magnetic moment is about 600 times that of Earth, whereas Jupiter's magnetic moment is 20,000 times greater than Earth's. The magnetosphere of Saturn, which takes on a teardrop shape around the planet, is primarily shaped by its own magnetic field instead of the magnetic fields found between planets. This significantly impacts how charged particles, mainly those from the Sun, behave within that region. The convex side of the teardrop faces the Sun, creating a boundary, or magnetopause, with the solar wind at around 20 Saturn radii, 1,200,000 kilometers, 750,000 miles, from the planet's center. However, This distance varies significantly due to fluctuations in solar wind pressure. A large magnetotail extends to significant distances on the far side of Saturn, altering the magnetosphere. Like the magnetospheres of Earth and Jupiter, Saturn's inner magnetosphere maintains a steady group of highly energetic charged particles, mainly protons, that move in spiral paths along magnetic field lines. The particles form rings encircling Saturn, similar to the Van Allen belts found on Earth. Unlike Earth and Jupiter, the uptake of particles on the surfaces of solid planets within the field lines greatly diminishes Saturn's number of charged particles. The data from Voyager showed the existence of holes in the particle populations along the field lines that intersect the rings and the orbits of moons within the magnetosphere. Titan and Hyperion, Saturn's moons, orbit close to the smallest limits of the magnetosphere and occasionally cross the magnetopause, moving outside of Saturn's magnetosphere. Charged particles in Saturn's outer magnetosphere collide with neutral atoms in Titan's upper atmosphere, energizing them and leading to atmospheric erosion. The Cassini orbiter observed a halo of highly energetic atoms. The ultraviolet auroras on Saturn are caused by charged particles from the magnetosphere hitting hydrogen atoms and molecules in its polar atmosphere. In the 1990s, the Hubble Space Telescope, in orbit around Earth, obtained ultraviolet photos of Saturn. The late 1990s and early 21st century successfully captured the auroral rings surrounding the poles. These offered clear evidence of the distinct symmetry of Saturn's magnetic field and explained how the auroras respond to the solar wind and the Sun's magnetic field. The low average density of Saturn indicates that its main makeup is predominantly hydrogen. Under the planet's circumstances, hydrogen exists as a liquid rather than a gas at pressures exceeding around 1,000 bar, which corresponds to a depth of 1,000 kilometers, 600 miles, 100 miles, beneath the clouds. At this level, the temperature is approximately 1,000 Kelvin, 1,340 degrees Fahrenheit, 730 degrees Celsius. It is very easy to compress molecular hydrogen even when it is liquid. In order to reach Saturn's average density of negative 6.9 grams per cubic centimeter, negative 4 ounces per cubic inch, pressures higher than 1 megabar are needed. This occurs at 20,000 kilometers, 12,500 miles, beneath the clouds, nearly one-third of the distance to the planet's core. Looking into Saturn's uneven gravitational field provides valuable information about its internal composition. The swift spinning of the planet and its low average density led to alterations in its physical form and gravitational influence. The exact shape of the field can be found by looking at how it changes the paths of nearby spacecraft and the arrangement of certain rings around Saturn. The distribution of mass within the core of Saturn, in contrast to its outer envelope, directly impacts the degree of distortion. The distortion analysis shows that Saturn is much more centrally condensed than Jupiter, meaning it has a significantly larger amount of material denser than hydrogen in its core. The central portions of Saturn comprise roughly 50% hydrogen by mass, whereas Jupiter's central regions contain about 67% hydrogen. We think that fluid molecular hydrogen will change into a fluid metallic state, similar to a molten alkali metal like lithium, when the pressure is about 2 megabars and the temperature is about 6,000 Kelvin, which is 10,300 degrees Fahrenheit, or 5,730 degrees Celsius. This change occurs approximately halfway between Saturn's cloud tops and its core. The planet's gravitational field gives us information that the metallic region has a density that is much higher than the density of pure hydrogen and the solar ratios of helium. The excess helium gathered from the planet's outer layers might clarify the increased density. Furthermore, current information might not determine the precise spread of substances denser than hydrogen and helium, which could have a combined mass reaching as much as 30 times Earth's within Saturn. We anticipate a small central core that gathers a composition of rock and ice equivalent to 10 to 20 Earth masses. If Saturn's outer core is made up of fluid metallic hydrogen with slow-moving circulation currents, as expected from heat rising to the surface and denser parts falling due to gravity, then there is enough dynamo activity to make the planet's magnetic field. As a result, the same mechanism that creates Earth's magnetic field is also responsible for Saturn's magnetic field. The dynamo theory suggests that the deep field, found close to the core in the dynamo zone, might show significant irregularity. Spacecraft, on the other hand, study the outer part of the field, which is very consistent and has a dipole axis that is roughly parallel to the rotational core. Theories say that a non-convecting, electrically conducting zone that rotates around the field lines makes the magnetic field lines around the axis of rotation more symmetrical before they meet the surface. Strong electric currents in the conductive core might explain the notable change in the rotation period of the magnetic field observed over the past 25 years. Saturn emits about 2 times the energy into space compared to what it absorbs from the Sun, mainly at infrared wavelengths that range from 20 to 100 micrometers, 0.0008 to 0.004 inches. This difference indicates that Saturn, similar to Jupiter, possesses an internal heat source. Saturn's internal energy production is similar to Jupiter's for every kilogram of mass. However, because Saturn has less mass than Jupiter, it had a lower total energy content when both planets were forming. The radiation at Jupiter's level suggests that some of its energy comes from a different source. A thermal evolution estimate suggests that Saturn might have developed a core ranging from 10 to 20 Earth masses, formed through the accumulation of ice-rich planetesimals. Furthermore, a significant amount of gaseous hydrogen and helium from the early solar nebula would have gapped due to gravitational collapse. Scientists suggest that Jupiter experienced a similar formation process, although it absorbed a much larger amount of gas. Both planets raised the gas to high temperatures, several tens of thousands of kelvins, during the acquisition process. Jupiter's current internal energy production can be understood as the leftover cooling of a planet that was once heated throughout the solar system's history of approximately 4.6 billion years. For Saturn, using this approach indicates that the planet's energy output likely decreased beneath the present level around 2 billion years ago. Helium has been theoretically precipitating from its solution in hydrogen, and its steady descent has released additional gravitational energy. As helium splits into droplets in the metallic phase of hydrogen and falls to lower levels, the potential energy changes into the kinetic energy of the movement of the droplets. Friction then reduces this motion, transforming it into heat, which radiates into space, increasing Saturn's internal heat supply. It is believed that Jupiter has experienced a comparable process, though to a lesser extent, because of its hotter interior and increased helium levels. The identification of a notable helium deficiency in Saturn's atmosphere by the Voyagers initially supported this idea. However, it has since faced skepticism. While they may appear distinct, the rings of Saturn and its moons form a complex system of objects marked by intricate interconnections, dynamic interactions, and evolutionary developments. The paths of the closest known satellites are located within or next to the farthest rings, while recently found moons remain part of the ring structure. The ring system contains many tiny moons, ranging from dust particles to objects comparable in size to cars and houses, each following its orbit around Saturn. Because of the difficulty in distinguishing the largest ring particles from the smallest moons, it may be impractical to determine the total count of moons orbiting Saturn. In 1610, Galileo's initial observations of Saturn through a rudimentary telescope led him to declare that Saturn is not a singular star, but rather a conglomerate of 3 bodies that nearly contact one another, remain stationary relative to each other, and are aligned linearly along the zodiac, with the central body being 3 times larger than the outer ones. 2 years later, he was perplexed that the image in his telescope had changed into a unique object. Earth had crossed Saturn's ring plane, and when seen from the side, the rings had nearly disappeared. Further observations showed Galileo that the fascinating side appendages had returned to view. He never suggested that the appendages formed a disk encircling the planet. In 1655, the Dutch scientist Christian Huygens commenced his observations of Saturn using an enhanced telescope, ultimately discerning the actual configuration of the rings and the significant inclination of the ring plane relative to Saturn's orbit. He insisted that the rings formed a unique solid disk of significant thickness. In 1675, the Italian-born French astronomer Gian Domenico Cassini discovered a significant gap, now referred to as the Cassini division, within the ring system, undermining the notion of a solid ring. In the year 1789, the French mathematician and scientist Pierre-Simon Laplace put forward a theory that indicated the rings were made up of many smaller particles. In 1857, Scottish physicist James Clerk Maxwell analytically established that the rings could only be stable if they consisted of many microscopic particles. A conclusion corroborated almost 40 years later by American astronomer James Keeler. While Saturn's rings are extensive, they are surprisingly slender. The principal rings possess a diameter of 270,000 kilometers, 170,000 miles. Yet their thickness does not surpass 100 meters, 330 feet, and their cumulative mass is around 3 times 10 to the power of 19 kilograms, 6.6 times 10 to the power of 19 pounds, roughly equivalent to the mass of Saturn's moon Mimas. The ring system extends almost 1 million kilometers when accounting for the feeble outer rings. Like other gas giants, the main rings of Saturn are located within the classic Roche limit. The ideal distance for a relatively large moon to move toward the center of its larger planetary parent before tidal forces break it apart is 2.4 Saturn radii, or 147,000 kilometers, 91,300 miles. Tidal forces, on the other hand, prevent small bodies within the Roche limit from merging into larger ones. The limit applies only to objects influenced by gravitational pull. It does not restrict the stability of a tiny entity whose molecular bonding exceeds the tidal forces that could break it apart. As a result, small moons and artificial satellites that are tens of kilometers in size or smaller can persist indefinitely within the Roche limit. Although the particles that make up Saturn's rings are not directly visible, we can deduce their size distribution by examining how they affect the scattering of light and radio signals sent through the rings from other celestial objects and spacecraft. This investigation shows a broad and ongoing variety of particle sizes, ranging from centimeters to several meters, with larger particles significantly less common than smaller ones. The distribution aligns with the expected outcome of repeated collisions and the breaking apart of initially larger objects. In specific areas of the rings where collisions appear more often, smaller particles akin to dust are present. However, these have short lifespans because of different loss mechanisms. The tiny particles of clouds appear to acquire electric charges, interact with Saturn's magnetic field, and manifest as lively, wedge-shaped spokes extending across the surface of the rings. While spokes were often seen during the Voyager missions, Cassini's initial orbits did not observe them, which may suggest that a different solar angle affected the creation of charged particles. Significant formations known as ring moons, which can be several kilometers wide, might be located within the main rings. However, only a few have been discovered. Evidence shows that the contrasting forces of gravity, collisions, and changing orbital speed within the dense rings continuously create and destroy temporary rubble pile moons. The rings beautifully bounce sunlight, and a detailed analysis of the light they reflect reveals the presence of water ice. As a result, the breakup of a moon similar in size and makeup to Mimas created the main rings. Many planetary scientists think that the breakup that caused the rings to form happened not too long ago, maybe within the last few tens of millions of years. The main ring system has structures at different sizes, from the three main rings that can be seen from Earth, C, B, and A, which are arranged in order of increasing distance from Saturn, to many smaller rings with widths of several kilometers. There is a lot to see. The structures have provided scientists a beneficial area for studying gravitational resonances and the combined effects of many small particles nearby. Although researchers have theoretically clarified various structures, many remain mysterious, and we have yet to achieve a complete system synthesis. Saturn's ring system might act as a model for the early disk of particles that gave rise to the planets. Therefore, understanding its dynamics and evolution holds important implications for the formation of the solar system. The optical depth of the rings, depending on the distance from Saturn, outlines their structure. A medium, which may include a cloud, a planet's atmosphere, or a region of particles in space, absorbs electromagnetic radiation measured as optical depth. As a result, it serves as an indicator of the average density of the medium. A completely clear medium has an optical depth of 0. As its density increases, its numerical value rises accordingly. The optical depth depends on the radiation's wavelength and the medium's properties. The smallest particles in Saturn's rings don't get in the way of radio waves that are several centimeters long or longer. This means that radio waves have lower optical depths than visible waves. The B ring stands out as the brightest, broadest, and most significant of all the rings. It ranges from 1.52 to 1.95 Saturn radii and exhibits optical depths between 0.4 and 2.5. The specific values are contingent upon both the distance from Saturn and the wavelength of light. The equatorial radius of Saturn measures 60,268 kilometers, 37,449 miles. The Cassini division, the most prominent gap in the main rings, clearly sets it apart from the outer major ring, the A ring. The Cassini division, located between 1.95 and 2.02 Saturn radii and composed of particles, exhibits complex variations in optical depth with an average of 0.1. The A ring spans from 2.02 to 2.27 Saturn radii and exhibits optical depths ranging from 0.4 to 1.0. The C ring, occasionally called the Crep ring, is the third significant ring found inside the B ring, positioned between 1.23 and 1.52 Saturn radii, with optical depths nearing 0.1. Within the C ring, at distances of 1.1 to 1.23 Saturn radii, resides the exceedingly sparse D ring, which exerts no discernible influence on starlight or radio waves traversing it, and is observable solely in reflected light. The narrow F ring is located beyond the A ring, at a distance of 2.3 Saturn radii. Cassini's discoveries show that the F ring is a complicated formation that resembles a tightly coiled spiral. A slender strip of substance, probably expelled by the inner moon atlas, is nestled between the A and F rings as it travels along its orbit. The delicate G ring, located approximately 2.8 Saturn radii away and having an optical depth of only 0.0001, is found even further out. Images from Voyager faintly unveil the mysterious G ring, linked to its influence on charged particles in Saturn's magnetosphere. Images captured by Cassini in 2008 disclose the existence of a diminutive moon within the G ring, designated Aegaeon, measuring approximately 0.5 kilometers, 0.3 miles in diameter. This moon might be one of the original bodies of the G ring, The outermost identified ring, the exceptionally wide and diffuse E ring, spans from 3 to 8 Saturn radii. Cassini's observations have shown that the E ring is made up of ice particles from geysers, which are a type of ice volcanism also known as cryovolcanism. The geysers are located in a thermally active area, or hotspot, close to Enceladus's south pole. Similar to Jupiter's rings, Saturn's rings, extending beyond the A ring, are mainly made up of tiny particles continuously emitted by its moons. There are important gaps in the optical depth distribution within the ring's main sections. Notable astronomers associated with Saturn studies have had important gaps named after them. Alongside the Cassini division, the gaps include the Colombo, Maxwell, Bond, and Dawes gaps, which are 1.29, 1.45, 1.47, and 1.50 Saturn radii, respectively, within the C ring. The Huygens gap at 1.95 Saturn radii at the outer boundary of the B ring, the Encke gap in the outer region of the A ring at 2.21 Saturn radii, and the Keeler gap, situated near the outer edge of the A ring at 2.26 Saturn radii. Among these gaps, only Encke was acknowledged before the spacecraft explored. After the Voyager missions, scientists hypothesized that a moon of 10 kilometers, 6 miles in diameter, circling within the gap zone, could exclude particles from an area to create a gap. The Voyager photographs revealed the moon pan located in the Encke gap in 1990, and the Cassini images later captured it again. Images from Cassini in 2005 identified the expected moon, Daphnis, located within the Keeler gap. Similar moons might exist in the Huygens and Maxwell gaps. Some concepts propose that a moon with an orbit that is notably inside or outside a ring can generate a gap in that region through orbital resonance. Resonance occurs when the orbital periods of the moon and the ring particles show a relationship of whole number ratios. In these cases, a specific ring particle will repeatedly come near the moon at the same locations in its orbit, and the gravitational effects on its path will build up over time, eventually forcing the particle to stray from perfect resonance. As the moon travels around the ring, it gathers angular momentum from the particles in the resonant ring, forming a tightly coiled spiral density wave within it. If the resonance is strong enough, this process can ultimately result in the creation of a gap. There is a 2-to-1 resonance with Mimas in the boundary region at the outer edge of the B ring and the inner edge of the Cassini division. This means that Mimas's orbital period is twice that of the ring particles at that radius. The resonance shows that the border isn't perfectly circular, displaying variations in radius that create a two-lobed shape. The location of this boundary clearly shows the effect of the resonance on the inner edge of the Cassini division, but our understanding of the division's complete structure remains unfinished. The co-orbital moons Janus and Epimetheus have a 7-to-6 resonance with the outer boundary of the A ring, which is characterized by 7 scalloped lobes. We observe similar resonances across the ring system, yet many associated features remain puzzling. It is important to find a lot more moons and resonances so that we can better understand Saturn's rings and their many ringlets and complex layers. Can you express the numbers in written form? Saturn possesses more than 60 acknowledged moons. Among the initial 18 moons of Saturn identified, all but the somewhat more remote moon Phoebe revolve around 3.6 million kilometers, 2.2 million miles, of Saturn. Before the 20th century, astronomers recognized 9 moons with a radius exceeding 100 kilometers, 60 miles, while an analysis of Voyager photographs uncovered the other moons in the early 1980s. The photos captured by the Cassini spacecraft began to reveal several additional inner moons, small bodies with radii varying from 3 to 4 kilometers, 1.9 to 2.5 miles. All inner moons have a consistent pattern, with forward-moving, low-angle, and low-variation orbits about the planet. like how planets formed around the Sun from the early solar nebula. Researchers believe Saturn's 8 largest moons came from a disk of material in the planet's equatorial plane. Beyond around 11 million kilometers, 6.8 million miles, we find a secondary outer group of moons. Their orbits show notable eccentricities and inclinations. Approximately 2/3 orbit Saturn in a retrograde manner, moving against the planet's rotation. Except for Phoebe, their orbital radii are less than 20 kilometers, 12 miles. In 2000, initiatives were launched to implement novel electronic detection techniques to identify certain objects from Earth, while Cassini uncovered additional ones. These external bodies are not original moons, but instead captured entities or their remnants. Some unusual and mysterious characteristics of Saturn's moons' orbital and rotational movements emerge from their interactions with the rings. It is said that the 3 small moons, Janus, Epimetheus, and Pandora, located at the outer edge of the main ring system, have gained angular momentum from ring particles through shared gravitational interactions. This method would reduce the spread of rings caused by collisions between ring particles and push these moons into wider orbits. Because of the small size of the moons, researchers have faced difficulties finding a mechanism that could maintain this process throughout the solar system's history without moving the moons considerably from their current positions. The unique shape of the outer edge of the main ring system and the current paths of inner moons like Atlas are confusing. This suggests that the current ring system is a lot younger than Saturn itself. Scientists call Pandora and her nearest moon, Prometheus, shepherd moons due to their influence on ring particles. During Voyager 1's flyby, Pioneer 11 identified the 2 planets orbiting on either side of the slender F ring just 1 year prior. The gravitational interactions of the moons with the F ring create a shepherding effect, confining the ring's particles to a limited region. Prometheus, the inner shepherd, gives angular momentum to the ring particles, pushing the ring outward and inward, while Pandora, the outer shepherd, takes in angular momentum from the ring particles, pulling the ring inward and outward. Cassini captured an extraordinary video of this phenomenon, showcasing how the shepherd moons draw out complex wave-like bands of particles from the F ring as they move through it. The term shepherd is often used to refer to any moon that uses gravitational forces to control the extent of a ring. In this wider context, moons like Janus and Epimetheus, which show ring effects as noted earlier, along with gap-creating moons like Pan, are similarly categorized as shepherds. Janus and Epimetheus are co-orbital satellites that share the same average orbit. Every few years, they come near to one another, interacting gravitationally in a way that one gives angular momentum to the other, causing the latter to rise to a marginally higher orbit, while the former drops to a slightly lower orbit. During the next close encounter, the procedure repeats itself in reverse. Tethys and Dione have co-orbital satellites. However, there is minimal angular momentum exchange because of their larger mass about these co-orbiters. Tethys has 2 co-orbiters, Callisto and Calypso, which are positioned in stable Lagrangian points along Tethys's orbit, leading and trailing by 60 degrees, much like the Trojan asteroids found in Jupiter's orbit. On average, Dion's Trojan companions, Helene and Polydeuces, precede and follow it by 60 degrees, respectively. A number of pairs of moons can be found in stable, dynamic resonances. This means that the moons in each pair pass each other on a regular basis as they orbit, interacting gravitationally in a way that keeps these meetings regular. The orbital periods of 2 moons are in a ratio of small whole numbers. At 21.28 days and 15.94 days, respectively, Hyperion's and Titan's orbital periods show a ratio of 4:3. This means that Titan makes 4 circles around Saturn while Hyperion only makes 3. Titan and Hyperion draw near one another at Hyperion's apoapsis, the farthest point of its elliptical orbit. The periodic shoves push Hyperion into a relatively extended, eccentric orbit as Titan, which has more than 50 times Hyperion's mass, consistently gives the greatest momentum to the smaller moon at the same points in its orbit. The moon's orbital periods, Dione and Enceladus and Tethys and Mimas, show a 2-to-1 ratio. The interactions between pairs of moons can lead to notable changes in their orbits, which may play a vital role in the geological development of the planets they influence. The gravitational interactions between Saturn and its nearby moons lead to cyclical changes in shape in one body due to the influence of the other. This process reduces the moon's eccentricity and aligns their rotation with Saturn's. The synchronous rotating state is common in the solar system, as shown by the moon of Earth and some of the nearby moons of Jupiter. The interior deformation of a moon that orbits its planet is dynamic. It experiences cyclical movement, generating heat through internal friction. When a moon reaches synchronous rotation, it always shows the same hemisphere to the planet, keeping the forward and backward hemispheres fixed in its orbit. The deformation stops moving in the moon's frame of reference, and frictional heating stops happening. But if resonance sends a moon into an eccentric orbit, even if its rotation is synchronous, it will experience tidal interaction. As it moves closer and farther away from its planet, it will deform dynamically, which will create heat inside it. Jupiter's Io is a prime example of a truly remarkable moon. Current calculations indicate that the tides on Saturn's moons do not serve as a significant heating source, although this may have varied in the past. Additionally, Enceladus's thermally active Tiger Stripe region is presently the source of icy material for the surrounding diffuse E-ring. We need to determine where the region's thermal activity is, likely due to tidal deformation. Hyperion is an extraordinary phenomenon where tidal forces drive moons to attain synchronized rotation. The orbital eccentricity and irregular shape of Hyperion, which is unusual for a body of its size, have led to a complex interaction between its spin and orbital angular momentum. Mathematically, we describe this interaction as chaotic in nature, even though the brief contacts from Voyager suggest that Hyperion rotates in a non-synchronous manner for about 13 days. The use of chaos theory on Voyager data and subsequent observations of Earth's moon show that it is actually tumbling erratically. Hyperion is the only celestial body in the solar system with chaotic rotation. Can you express the numbers in written form using words? Titan is Saturn's largest moon and the only moon in the solar system known for having clouds and a thick atmosphere. In 1655, the Dutch scientist Christian Huygens discovered Titan through a telescope, marking it the first planetary satellite following Jupiter's 4 Galilean moons. The moon derives its name from the Titans of Greek mythology, such as Cronus, who is associated with the Roman god Saturn and his 11 brothers and sisters. Titan appears as a mostly uniform brownish-red sphere when viewed through a telescope on Earth, its surface perpetually hidden by a thick haze. It is larger than Mercury and has a greater mass than Pluto. In some ways, it looks more like a planet than a typical moon. Titan circles Saturn at an average distance of 1,221,850 kilometers, 759,220 miles, completing one round in 15.94 Earth days. It completes one rotation on its axis for each revolution, showing that it rotates in sync. Titan consistently shows the same side as Saturn and keeps the same leading face as it orbits. The solid body of Titan has a diameter of 5,150 kilometers, 3,200 miles, approximately 120 miles larger. Titan is approximately 150 kilometers, 75 miles, smaller than Ganymede, Jupiter's largest and biggest moon in the solar system. However, when considering its vast atmosphere stretching hundreds of kilometers, Titan's size greatly surpasses that of Ganymede. Titan has an average density of 1.8 grams per cubic centimeter, which is 1.1 ounces per cubic inch. This means that its interior is likely made up of a mix of rock and frozen substances, possibly with ammonia, water, and methane. There may be liquid layers below a solid crust, mostly made of water ice. At the center, a rocky core could reach up to 80% of the entire radius. The characteristics of Titan's mass are similar to those of large icy moons found in the outer solar system, such as Ganymede and Callisto from Jupiter, as well as Triton, the largest moon of Neptune. The atmosphere of Titan. The Dutch-American astronomer Gerard P. Kuiper was the first to identify Titan's atmosphere through spectroscopy in 1944, uncovering evidence of methane absorbing sunlight. Nonetheless, studies on the bending of radio waves in the atmosphere during Voyager 1's flyby in 1980 revealed that methane molecules make up only a tiny fraction of the overall molecular makeup. In contrast, the main molecules stay invisible in visible light spectra. Taking a look at both infrared and radio data from Voyager together showed that the molecules in the atmosphere have an average molecular weight of 28.6 atomic mass units. So, Voyager found that molecular nitrogen, which has an average molecular weight of 28.8, was most likely the main component. However, atomic argon, which has an average molecular weight of 36, may also be present. Voyager discovered additional elements in Titan's atmosphere by absorbing ultraviolet light from the Sun, such as molecular hydrogen and various carbon-based compounds. Solar UV radiation is believed to interact with methane and nitrogen at high altitudes, leading to these effects. These include carbon monoxide and carbon dioxide and the organic gases, ethane, propane, acetylene, ethylene, hydrogen cyanide, diacetylene, methylacetylene, cyanoacetylene, and cyanogen, all found in trace amounts. Can you express the numbers in written form using words? Titan's atmosphere is similar to Earth's, particularly in its nitrogen gas composition and surface pressure, which is approximately 1.5 bars, exceeding Earth's sea level pressure by 50%. Nevertheless, the atmosphere of the Moon is significantly cooler, with a surface temperature of 94 Kelvin, minus 290 degrees Fahrenheit, minus 179 degrees Celsius, and devoid of free oxygen. A troposphere similar to Earth's extends from Titan's surface to an elevation of 42 kilometers, 26 miles, when a minimum temperature of 71 Kelvin, minus 332 degrees Fahrenheit, minus 202 degrees Celsius, is attained. The absence of nitrogen clouds is due to temperatures consistently surpassing the nitrogen condensation point. Initial findings from the Cassini-Huygens mission, which began its exploration of the Saturnian system in 2004, suggest that methane is a modest but important part of the atmosphere, possibly similar to water vapor in Earth's troposphere. About 5% of the air molecules at Titan's surface are made up of methane, and this proportion decreases as altitude increases. The lower atmosphere of Earth generally consists of about 1% water vapor. During its first meeting with Titan, Cassini observed a notable outburst of methane cumulus clouds in the southern polar region of Titan. Indirect evidence indicates that methane rain may sometimes fall close to the surface. In contrast to Earth, Titan lacks a liquid methane ocean, as this would require an atmospheric mixing ratio of 12%, which is inconsistent with the data that has been observed. Above the troposphere, Titan's atmosphere is made up of a thin layer that keeps the temperature pretty stable. Next is the stratosphere, which is made up of a layer that goes from 50 to 200 kilometers thick and has temperatures that rise gradually with height until they reach a maximum of minus 122 to minus 136 degrees Fahrenheit, minus 133 to minus 93 degrees Celsius. Research on the refraction of starlight in Titan's upper atmosphere indicates that temperatures persist within this range up to 450 kilometers. 280 miles. At the same time, spacecraft investigations of solar ultraviolet light transmission reveal comparable values at much greater altitudes. Can you express the numbers in written form? Titan's veiling haze may be made up of aerosols of complex organic substances that are constantly being made when the sun's ultraviolet radiation interacts with the nitrogen-methane atmosphere. These tiny particles soak up sunlight and add to the rich brownish-red color. These particles are everywhere in Titan's atmosphere, keeping a notable density even at 300 kilometers, 200 miles heights, and pressures below 1 millibar. The Huygens entrance probe detected haze particles while descending through the troposphere to a height of approximately 30 kilometers, 20 miles. Particle dimensions range from 0 to 1 micrometer, 0.004 inches. Evidence shows that the density of these particles varies with the seasons, rising in Titan's summer hemisphere because of solar light. The solar heating of particle layers creates a temperature inversion layer in Titan's stratosphere, preventing the smog layer from dissipating through convection. The haze particles are believed to slowly fall through the atmosphere and accumulate on Titan's surface. Titan's history has led to an ongoing accumulation of organic materials covering the whole surface to a depth of at least several hundred meters. Titan's atmospheric composition and intricate organic compounds suggest that the Moon might function as a laboratory for exploring the different types of organic molecules and the chemical processes that played a role in the emergence of life on Earth 4 billion years ago. Scientists consider Titan's nitrogen-rich atmosphere to be secondary, akin to Earth's, rather than primordial. It probably came from the photochemical decomposition of ammonia, a common ice found in the outer solar system, into molecular nitrogen and hydrogen. The ability of a large moon such as Titan to sustain a substantial atmosphere over billions of years depends on a delicate balance between surface gravity, atmospheric molecular weight, and solar radiation. The stronger gravitational attraction between the Moon and an air molecule results in a longer retention time. On the other hand, a warmer atmosphere increases the likelihood of the molecule escaping into space. The Galilean moons of Jupiter and Earth's moon are too warm to retain significant gases, while the cold Titan and the adequately large Earth have managed to preserve nitrogen molecules. Neither Titan nor Earth has retained the lighter hydrogen molecule. The expanse. Before the Cassini-Huygens mission, limited information about Titan's surface was available. Because the Moon's haze allows some near-infrared light to pass, earlier telescopic studies using this feature showed that the surface is not uniform. In 1994, images taken in near-infrared wavelengths by the Hubble Space Telescope revealed a bright, continent-sized region, later named Xanadu Regio, on the leading hemisphere of Titan. The radar frequencies that passed through the haze allowed Earth and the Cassini probe to pinpoint this location. While orbiting Saturn, the Cassini spacecraft carried out numerous observations during a sequence of close flybys of Titan beginning in the late 2004. On the 14th of January, 2015, the Huygens entry probe became the first spacecraft to land on a planetary surface in the outer solar system. The mission carried out multiple physical and chemical examinations of Titan's atmosphere and transmitted detailed images while descending with its parachute. The Cassini-Huygens mission showed that Titan's surface is young, featuring only a few notable impact craters. Wind and likely rain, similar to liquid methane, mold Titan's surface in a way that is reminiscent of Earth's. Channels called rivers are often bordered by dark hydrocarbon deposits, sometimes crossing faults and frequently featuring extensive tributary systems. Cat scratches, elongated dark structures oriented east-west that extend for hundreds of kilometers, may represent dunes of dark particle matter. In contrast to expectations of lakes and oceans, we have clearly noted the absence of surface liquids on Titan. Can you express the numbers in written form using words? Mimas is the tiniest and closest of Saturn's main regular moons. The English astronomer William Herschel discovered it in 1789 and named it after a giant from Greek mythology, Gigantes. Mimas has a diameter of approximately 400 kilometers, 250 miles. It orbits the planet in a prograde, nearly circular trajectory at an average distance of 185,520 kilometers, 115,277 miles. Because of tidal interactions with Saturn, the Moon shows synchronous rotation with its orbital movement, always displaying the same side towards Saturn while advancing with that side in its orbit. The average density of Mimas is just 1.1 times that of water, and its surface shows characteristics of water frost. The evidence substantiates the assertion that Mimas primarily consists of ice. The surface shines brightly and is largely defined by deep, bow-like impact craters. The depth of the craters comes from a lack of surface gravity, which is clearly not enough to cause slumping. Even though it is small, Mimas shows evidence of resurfacing, possibly because of the partial melting of its icy surface. The most significant characteristic is the Herschel crater, which has a diameter of 130 kilometers, 80 miles, and is located in the center of the leading hemisphere. The crater's outside walls rise 5 kilometers, its bottom descends 10 kilometers, and the central peak reaches 6 kilometers. Herschel ranks as one of the most significant impact structures, comparable in size to the celestial bodies recognized within the solar. Mimas is in an orbital resonance with the more distant Saturnian moon Tethys. Its 22.6-hour orbit around Saturn is half that of Tethys, resulting in the two bodies consistently approaching each other on the same side of Saturn. This resonance is not by chance. Based on the principle of conservation of momentum, it probably began with a slow process, like how tidal friction slows down Saturn's spin. This caused the paths of both moons to get wider, with Mimas growing faster than Tethys over geological time. Mimas is in orbital resonance with several acknowledged structures within Saturn's ring system. The Cassini divide is a big space with lower particle density in the main rings and an orbital period about half that of Mimas. The inner boundary of the divide is set by the interactions between ring particles and the Moon. Extra ring orbits that resonate with Mimas show bending waves, closely wound spiral waves of ring material displaced above or below the ring plane. Can you express the numbers in written form using words? Enceladus is the second nearest of Saturn's main regular moons, and the brightest of all its moons. In the year 1789, the English astronomer William Herschel discovered it, naming it after one of the giants from Greek mythology, known as Gigantes. Enceladus has a diameter of approximately 500 kilometers, 310 miles, and circles Saturn in a prograde, almost circular trajectory at an average distance of 238,020 kilometers, 147,899 miles. Its average density is just 30% more than water's, suggesting it comprises at least 50% water ice. The surface of Enceladus shows a greater reflectivity than newly fallen snow. Images from Voyager showed that there weren't many big craters. Instead, there were smooth, crater-free areas and wide, ridged plains that strongly suggested that the planet's interior had been active not long ago, maybe in the last 100 million years, causing a lot of melting and resurfacing. Spectral measurements from Cassini show that the surface of Enceladus is mainly made up of water ice. Before the flyby of the U.S. spacecraft Voyager 2 in 1981, no information was available about Enceladus. The probe, coming within 87,140 kilometers, 54,146 miles, captured photos indicating that Enceladus possesses a complex geological structure. having experienced 5 separate evolutionary phases. In 2005, Cassini initiated a sequence of close flybys of Enceladus, approaching within 200 kilometers, 125 miles. These observations confirmed that some parts of the Moon are currently experiencing geological activity. These areas are characterized by very high heat flow, higher than what was expected from solar heating alone, and the release of water vapor and ice from geysers, which is known as cryovolcanism. This is most noticeable in the southern polar region. The Moon's southern polar hotspot registers a temperature of 140 Kelvin, minus 208 degrees Fahrenheit, minus 133 degrees Celsius, and features perplexing geological formations called tiger stripes. A lot of the areas without craters may only be 100 million years old. This means that parts of the surface have been melting and refreezing recently, which means that Enceladus may have more than one active zone. The continuous activity of Enceladus produces Saturn's E-ring, a fine ring made up of tiny water ice particles that originate from vapor released by the geysers. The particles are mostly gathered close to Enceladus's orbit and look a lot like the cloud of orbital particles released from Io, Jupiter's volcanically active moon. Cryovolcanic eruptions regularly change the orbital lifetimes of E-ring particles, which can be as short as 10,000 years. Enceladus ejects water ice particles, contributing to the E-ring at around 1,000 metric tons yearly. Like Europa, the possible existence of liquid water in Enceladus makes it a promising environment for life. Enceladus's 33-hour orbit around Saturn is half that of the more distant moon Dione, indicating an orbital resonance between the two celestial bodies. In some situations, this kind of resonance can cause a lot of tidal heating for the inner moons involved. However, more complex calculations are needed to show how this mechanism could produce enough heat to explain what is going on in Enceladus. A significant divide surrounds most of Tethys. The Italian-born French astronomer Gian Domenico Cassini discovered Tethys in the year 1684 and named it after a Titan from Greek mythology. Tethys has a diameter of 1,060 kilometers, 659 miles, and a density of 1.0 grams per cubic centimeter, 0.58 ounces per cubic inch, which is the same as that of water, indicating that it is made up entirely of ice. It orbits Saturn in a prograde, circular trajectory at 294,660 kilometers, 183,090 miles, within the planet's extensive tenuous E-ring. It involves an orbital resonance with the nearby moon, Mimas, such that Tethys finishes one orbit lasting 45 hours for every 2 orbits of Mimas. Tethys shows synchronous rotation with its orbital period, keeping a steady orientation toward Saturn while displaying the same face during its path. 2 small moons, Callisto and Calypso, named after the daughters of Titans, accompany Tethys, maintaining gravitationally stable positions along its orbit, similar to Jupiter's Trojan asteroids. Callisto is 60 degrees ahead of Tethys. Calypso is 60 degrees behind. Tethys shows very few signs of internal activity. The most remarkable characteristic is Ithaca Chasma, a vast fissure several kilometers deep that spans 3/4 of the moon's circumference and constitutes 5 to 10% of its surface area. Researchers propose that the heavily pockmarked elevations encircling the formation indicate the chasm's ancient geological evolution. The story began when the water inside froze and expanded. A second significant characteristic is the Odysseus crater, which spans 400 kilometers, 250 miles in diameter, and contains a prominent central peak. The high concentration of impact craters on Tethys suggests that the surface is ancient. However, the surface exhibits considerable reflectivity, especially on the leading hemisphere of Tethys, which is unusual for geologically ancient surfaces. Planetary scientists think that the surface brightness distribution is changed by the buildup of micrometer-sized ice particles from Saturn's E-ring, where Tethys is deeply embedded. The discovery that many craters on Tethys have bright floors, unlike the dark-floored craters found on Saturn's moon Hyperion, which orbits farther away from Tethys and the E-ring, is put forward as evidence. Gian Domenico Cassini, a French astronomer of Italian descent, discovered Dione in the year 1684 and named it after a daughter of the Titan Oceanus from Greek mythology. Dione is in the outer part of Saturn's sparse E-ring. It has a diameter of 1,120 kilometers, 696 miles, and orbits the planet around it on a prograde, nearly circular path that is 377,400 kilometers, about 234,500 miles, wide. Two small moons, Helene and Polydeuces, named after characters from Greek mythology, accompany Dione in its orbit. Helene, with a diameter of approximately 30 kilometers, 20 miles, occupies a gravitationally stable position 60 degrees before Dione. Polydeuces, having a diameter smaller than half of Helene's, followed Dione by 60 degrees, even though it shows significant variations from its typical position. We can compare the paths of these small partner moons with those of Jupiter's Trojan asteroids. The gravitational pull from Saturn has slowed down Dione's rotation, causing it to rotate in sync with its orbit. This means that Dione always shows the same side to Saturn, while also moving through its orbit with that same side leading the way. The surface of Dione shows notable variations in brightness, where the trailing hemisphere is generally darker than the leading hemisphere. Dione's high average reflectivity suggests a surface rich in geologically freshwater ice. The moon's low density, 1.5 times that of water, aligns with a bulk composition of approximately equal proportions of ice and rock. Dione is heavily characterized by impact craters, and the density and size distribution of these craters suggest a geological age of 4 billion years. On the other hand, in some areas, the number of craters is lower, suggesting that the moon might have experienced considerable ice melting and resurfacing. New ice particles from the E-ring might keep building up on Dione's surface. The bright, notable half of Dione features the majority of its craters. Many bright, straight formations create a network of polygons, dividing the opposite hemisphere. The episodic movement of tectonic plates caused some remarkable features associated with long, narrow valleys and elevated areas. Pictures from the Voyager spacecraft revealed intricate shapes, showcasing layers of recondensed volatile materials flowing from straight cracks in Dione's core. Nonetheless, high-resolution images from the Cassini mission show no signs of such activity. Even though there are signs of a notable impact near the center of the linear network on the backside of the moon, the unevenness of its surface continues to be unclear. Like various objects orbiting Saturn, Dione engages in an orbital resonance. In particular, its orbit around Saturn lasts 66 hours, double that of the nearer moon Enceladus. This link has been proposed as a reason for the notable tidal heating seen in Enceladus. However, the details of this process need more clarification. Rhea is the second largest moon of Saturn after Titan. The Italian-born French astronomer Gian Domenico Cassini discovered it in 1672 and named it after a Titan from Greek mythology. Rhea is 1,528 kilometers, 99 miles, across, and goes around Saturn in a nearly circular backwards-pointing path that is 527,490 kilometers, 327,490 miles, wide. Its orbit lasts for about 4.5 Earth days. The density of Rhea, 1.3 times that of water, indicates that the moon is predominantly composed of ice. Furthermore, infrared spectral data suggest a surface predominantly covered in water frost. Similar to many of Saturn's notable moons, Rhea shows synchronous rotation with its orbital period, keeping one hemisphere consistently facing Saturn while the same hemisphere moves forward in its orbit. The surface of Rhea shows notable reflectivity, and there are clear regional variations present. Rhea is similar to Saturn's moon, Iapetus, in size and density. However, its surface brightness distribution differs from that of Iapetus and is less prominent. In this regard, it resembles its neighboring moon, Dione. Its foremost hemisphere is bright and heavily cratered, whereas its trailing hemisphere is more shadowy, showcasing stunning wispy lines, a lack of craters, and signs of resurfacing. At Saturn's distance from the Sun, frozen water and other volatile materials solidify, showing mechanical properties similar to rock, which helps to preserve impact craters. Therefore, Rhea's bright, pockmarked surface resembles the heavily cratered highlands of Mercury or the moon of Earth. Rhea is the most extensively cratered moon of Saturn, and the reflective qualities of its surface indicate that it has considerable porosity, similar to the regolith created by impacts on the moon. Scientists have observed bright lines on the shadowy trailing side of Rhea. Tectonic activity like faulting or the release of volatiles like water or methane through cracks and then their deposit on the surface are likely to cause the streaks. While orbiting Saturn, the notable side of Rhea displays a remarkably bright crater with vast shining rays extending over a significant portion of the surface, similar to the famous rayed lunar crater Tycho. Hyperion, characterized by its distinctive absence of a steady rotation period and seemingly unpredictable tumbling motion, is a celestial object that captivates the interest of astronomers. Independently found by astronomers from America and England, it received its name from a Titan in Greek mythology, which adds an element of mystique to its already fascinating character. Hyperion orbits Saturn every 21.3 Earth days in a prograde direction at a distance of 1,481,100 kilometers, 920,300 miles, situated between the orbits of the moons Titan and Iapetus. Hyperion's orbit stands out because of its unusual shape, exhibiting a significant elongation, and it is tilted at an angle of less than half a degree from the plane of Saturn's equator. The closer moon, Titan, completes 4 circles around Saturn for every 3 orbits of Hyperion, establishing a 4-to-3 dynamic resonance, with the 2 moons nearing each other most closely when Hyperion is at its apogee. In this situation, Titan, the larger body, exerts regular gravitational influences on Hyperion, causing it to follow a rather elongated orbit. Another feature of Hyperion is its irregular shape. People sometimes compare it to a large hamburger patty, with dimensions of 370 by 280 by 225 kilometers, 230 by 174 by 140 miles. It is the largest recognized moon with a distinctly uneven morphology. The reflectivity of 30%, which is moderately elevated, aligns with some water frost on its surface. Hyperion shows a reddish hue similar to the enigmatic dark areas on the distant moon Iapetus. Hyperion's average density is roughly 1/2 that of water ice, suggesting that the moon's interior may have a sparse arrangement of ice fragments mixed with voids. This structure might clarify the remarkable spongy look of specific areas on Hyperion's cratered surface, as seen in images captured by the Cassini spacecraft. Hyperion's unusual shape and erratic orbit hinder its ability to sustain a consistent rotation around a stationary axis. Rather, it showcases a distinct chaotic rotation, changing its rotational characteristics over intervals as short as 1 month. The uncertainty that sets it apart from every other celestial body in the solar system enhances the fascination surrounding Hyperion. Theoretically, it can rotate in a seemingly regular manner for thousands of years, followed by long periods of chaotic tumbling, rendering its rotation at any given moment completely unpredictable. Iapetus. Iapetus, the outermost of Saturn's principal regular moons, presents a celestial enigma because of its notable difference in surface brightness. Found by a French astronomer with Italian roots in the year 1671, it was named after a Titan from Greek mythology, adding intrigue to its already puzzling essence. Iapetus has a radius of 718 kilometers, 446 miles, and completes an orbit around Saturn every 79.3 Earth days at a distance of 3,561,300 kilometers, 2,212,900 miles. A 1.0 grams bulk density per cubic centimeter indicates that ice constitutes most of its composition. Saturn's inner moons orbit within 1 degree of the planet's equatorial plane. However, as you move past Iapetus, Saturn's equatorial bulge's gravitational pull weakens, letting the moon's orbits become more inclined. Researchers suggest that the average inclination of Iapetus, which is 15 degrees, is a remnant of the tilt from the now extinct gaseous disk that formed Saturn's main regular moons. The gravitational interactions with Saturn have aligned Iapetus's rotation to match its orbit around the planet. As a result, the moon always shows the same side as Saturn and continuously keeps the same face throughout its orbit. Interestingly, the front side shows significant darkness, reflecting only a tiny portion of the incoming sunlight, while the backside displays up to 10 times more reflectivity. The reflectance at the poles is significantly higher. Iapetus exhibits the most distinct differences in brightness compared to all acknowledged celestial objects. The solar system is a complex system. Cassini observed that as Iapetus circled Saturn, he could see it from one side but not the other, and he correctly theorized the reason behind this occurrence. Regardless of the United States, the Voyager spacecraft flybys revealed impact craters only on the bright trailing side of Iapetus, while later high-resolution images from the Cassini mission also showed craters on the leading side. The surface composition on the illuminated side is mainly pure water ice, possibly mixed with other forms of ice. The thick layer of complex organic materials, combined with iron-rich minerals altered by water, envelopes the red surface of the shadowy side. The difference in reflectivity arises from dark material made up of particles from the Saturnian system that have gathered on the moon's leading hemisphere. This material takes in more sunlight, warming the area enough to cause significant sublimation of water ice over long periods of geological time. The water vapor condenses on the trailing hemisphere and transforms into a solid state. The Cassini mission captured images of a remarkably slender ridge encircling a substantial section of Iapetus's equator. Models suggest that the actions of a slender dynamic ice lithosphere formed this ridge as the moon's deeper layers experienced heating. On the other hand, the observable impact basins of the moon and its various topographical features frequently require a more substantial lithosphere. The rapid changes in temperature on the moon during its first million years probably influenced most of its characteristics. Can you express the numbers in written form, please? Phoebe is a medium-sized, irregular satellite of Saturn, distinguished by its unique characteristics. Found in 1899 by an American astronomer, it was named after a Titan from Greek mythology, adding a touch of fascination to its already intriguing nature. Phoebe is about spherical, with a diameter of 220 kilometers, 136 miles, and an average distance from Saturn of 12,952,000 kilometers, 8,050,000 miles, significantly greater than that of Saturn's other main moons. It takes approximately 1.5 Earth years to complete one orbit around Saturn. The orbit is significantly eccentric, retrograde, and sharply inclined compared to the plane of Saturn's rings and its typical moons. Phoebe's surface shows notable differences in reflectivity, yet it remains mostly dark. Infrared measurements reveal water ice particles mixed with a black substance that looks a lot like the carbon-rich materials discovered on old C-class asteroids. Some lunar craters show signs of layers of bright and dark materials alternating. Phoebe has a mean density of about 1.6 times greater than that of pure water ice, surpassing the density of most of Saturn's notable icy moons. Based on this finding and Phoebe's strange orbital features, many scientists think that the moon did not form in orbit around Saturn, but instead evolved far from the Sun, where temperatures and the carbon-oxygen chemistry changed over time. It is not feasible to resolve objects on Saturn that are smaller than a few thousand kilometers, even in the best telescopic viewing conditions from the surface of Earth. Consequently, spacecraft exploration largely overlooked the complex features of the rings and atmosphere. German astronomer Johann Franz Encke documented the Encke gap within the A-ring in 1837. It was uncertain for almost 100 years, until American astronomer Harold Reitzema confirmed it in 1978 by using observations from an eclipse of the moon Iapetus by the rings to improve typical Earth-based resolution. Modern studies of Saturn from our planet's proximity rely on expert telescopic techniques. The analysis of infrared spectra from the rings, atmosphere, and moons has yielded important information regarding their composition and thermal balance. We achieve the spatial resolution of the rings and atmospheric structures on a scale of 1,000 meters by detecting light from bright stars that pass behind the planet as seen from Earth. In 1989, Saturn and Titan occulted the luminous star 28 Sagittarii, enabling scientists to examine ring and atmosphere structures with unprecedented detail since the Voyager missions. Surface-based telescopes and the Hubble Space Telescope successfully observed the emergence of the Great White Spot in Saturn's atmosphere in 1990, unimpeded by the distortions of Earth's atmosphere. In 1995, Earth passed through the ring plane, giving scientists a view of the ring from the side. This allowed them to get a good idea of how thick the ring was and how fast Saturn's rotational axis was moving off track. Pioneer 11 was the inaugural spacecraft to explore Saturn, the United States. It was one of 2 probes launched in the early 1970s to explore Jupiter. Even though retargeting wasn't part of the original goal, mission scientists took advantage of Pioneer 11's closeness to Jupiter's gravitational field to adjust the spacecraft's trajectory, leading to a successful flyby of Saturn. In 1979, Pioneer 11 traversed Saturn's ring plane at merely 38,000 kilometers, 24,000 miles, from the A-ring and approached within 21,000 kilometers, 13,000 miles, of its atmosphere. The United States Voyager 1 and Voyager 2, the pair of spacecraft, were first launched in the direction of Jupiter in 1977. The Voyager 1 and 2 spacecraft from the United States were outfitted with advanced imaging equipment designed for flybys of multiple planets and to accomplish specific scientific objectives at each site. Like Pioneer 11, Voyagers 1 and 2 used Jupiter's gravitational pull in gravity assist maneuvers to change their paths towards Saturn, which they arrived at in 1980 and 1981. The 2 spacecraft sent many images of Saturn, its rings, and its moons. The United States, European, and Italian space agencies launched the Cassini-Huygens mission in 1997. The spacecraft followed a complex path that included 2 gravity-assist flybys of Venus and Earth and Jupiter, ultimately arriving in the Saturnian system in the middle of the year 1004. The interplanetary craft, loaded with propellants, weighed over 6 metric tons and was among the largest, most costly, and most intricate constructed then. The mission included a Saturn orbiter, Cassini, intended for an extensive study of the planet, its rings and moons, and a probe, Huygens, which parachuted through Titan's atmosphere to achieve a solid surface touchdown in the early 2005. Huygens sent measurements and photographs to Cassini for approximately 3 hours during its descent, and from the surface, relaying them to scientists on Earth. Can you express the numbers in written form? Uranus, the seventh planet from the Sun, is situated beyond Saturn and is the least massive of the solar system's four large or Jovian planets: Jupiter, Saturn, and Neptune. At its brightest, Uranus is visible to the unaided eye as a blue-green dot of light. Greek mythology calls Uranus the sky's sun and Gaia's partner. A telescope discovered Uranus in 1781, making it the first planet not recognized in ancient times. The telescope has observed Uranus numerous times over the last 100 years, yet it was considered just another star. Its average distance from the Sun is around 2.9 billion kilometers, 1.8 billion miles, exceeding 19 times the distance from Earth, and it never comes closer to Earth than roughly 2.7 billion kilometers, 1.7 billion miles. Uranus, similar to the other gas giants, mainly consists of hydrogen, helium, water, and various volatile compounds due to its relatively low density, approximately 1.3 times that of water, and significant size, 4 times the radius of Earth. Hence, it lacks a solid surface. Methane in Uranus's atmosphere absorbs red wavelengths of sunlight, giving the planet a blue-green appearance. Most planets revolve at an angle nearly perpendicular to their orbits around the Sun. The axis of Uranus is roughly parallel to its orbital plane, causing the planet to rotate nearly on its side, with its poles shifting in orientation toward the Sun during its orbit. Additionally, the rotation axis and the center of the planet significantly tilt the axis of the planet's magnetic field. Uranus has approximately 20 moons, 5 relatively large, in addition to a system of thin rings. The Voyager 2 probe of the United States conducted the sole spacecraft visit to Uranus in 1986. Before that period, astronomers had a restricted understanding of the planet due to its distance from Earth, making it challenging to observe its visible surface, even with the most sophisticated telescopes. Efforts on Earth to determine a basic characteristic, like the time it takes for a planet to rotate, produced results that varied greatly, ranging from 24 to 13 hours, until Voyager 2 finally established a rotation period of 17.24 hours for the interior of Uranus. After Voyager's visit, improvements in ground-based observational technologies have deepened our comprehension of the Uranian system. At Uranus's distance from the Sun, the planet requires a little over 84 Earth years, approximately the duration of a human lifespan, to complete one orbit. The orbit's eccentricity is low, showing minimal deviation from a perfect circle, and the orbital inclination to the ecliptic, which is the plane of Earth's orbit and nearly that of the solar system, is less than 1 degree. The solar system planets generally show low orbital eccentricity and inclination levels, except for Mercury and Pluto, which stand out as notable exceptions. Researchers claim that collisions and gaseous drag reduced energy from the orbits during planetary formation, lowering the eccentricities and inclinations to their present values. Consequently, Uranus joined the other planets shortly after the formation of the Sun, approximately 4.6 billion years ago. Uranus and its closest neighbor, Neptune, the next planet from the Sun, are nearly the same in size. At the atmospheric pressure of 1 bar, corresponding to Earth's sea level pressure, Uranus's equatorial radius of 25,559 kilometers, 15,882 miles, exceeds Neptune's by 3.2%. Nonetheless, Uranus has only 85% of Neptune's mass, significantly reducing density. The difference in their bulk densities, 1.2, 8.5, and 1.64 grams per cubic centimeter, respectively, indicates a fundamental distinction in composition and interior structure. Even though Uranus and Neptune are significantly larger than the terrestrial planets, their radii are still under 50% of the largest planets, Jupiter and Saturn. The spin axis of Uranus is not at a right angle to the ecliptic, causing one pole to point upwards and the other downwards. The terms above and below refer to the same sides of the ecliptic as the north and south poles of Earth, respectively. International agreements define the north pole of a planet as the pole located above the ecliptic, regardless of the direction of its rotation. This description indicates that Uranus rotates in a clockwise direction, or retrogradely, around its north pole, which differs from the prograde rotation observed on Earth and most other planets. During Voyager 2's flyby of Uranus in 1986, the North Pole was shrouded in darkness, while the Sun was nearly positioned precisely above the South Pole. In 42 years, or half of a Uranian year, the Sun will position itself nearly directly overhead at the North Pole. The most popular theory says that Uranus's axis tilted a lot during the last stages of planet formation, when bodies about the size of planets today were involved in a number of catastrophic impacts that caused the planet to be tilted so far to the side. An alternative hypothesis suggests that a moon the size of Mars, orbiting Uranus in a retrograde direction, eventually collided with the planet, resulting in a tilt on its axis. Voyager 2 identified radio wave emissions with a rotation period of 17.24 hours, emanating from charged particles confined within the planet's magnetic field. After measuring the direct field, it was found to be tilted 58 degrees with respect to the rotation axis. It also moved around for 1724 hours. We propose that the field originates from the electrically conductive core of the planet. The swift spinning causes a bulging effect, compressing the planet's poles, resulting in a polar radius roughly 2.3% smaller than the equatorial radius. The winds in the atmosphere cause the clouds to rotate across the planet's visible surface, with durations ranging from 18 hours close to the equator to just over 14 hours at higher latitudes. The atmosphere. The main elements that make up the atmosphere of Uranus are molecular hydrogen and atomic helium. The planet's clouds spread sunlight from Earth, allowing for the identification of hydrogen. The bending of Voyager 2's radio signal by the atmosphere as the spacecraft passed behind the planet determined the ratio of helium to hydrogen. Helium makes up 15% of the total number of hydrogen molecules and helium atoms, corresponding to 26% by mass of the overall amount of hydrogen and helium. These values correspond with the Sun and surpass those of Jupiter and Saturn's atmospheres. It is believed that all 4 large planets obtained the same proportions of hydrogen and helium during their formation, with Jupiter and Saturn experiencing some helium settling toward their centers. Theoretical research suggests that the mechanisms responsible for this settling do not operate on less massive planets like Uranus and Neptune. Even though methane molecules only make up 2.3% of all molecules, they absorb a lot of light in the near-infrared range, which means they dominate that part of the reflected light spectrum. Astronomers derived this estimate of methane abundance by examining Voyager 2's radio transmissions, which reached atmospheric levels where the methane-to-hydrogen ratio is anticipated to stay consistent. If this consistency is typical of the planet, the carbon-to-hydrogen ratio of Uranus is 24 times greater than that of the Sun. Methane is made up of 1 carbon atom and 4 hydrogen atoms. The higher carbon-to-hydrogen ratio indicates greater oxygen, nitrogen, and sulfur abundance than solar values. These elements are associated with molecules of water, ammonia, and hydrogen sulfide, which are believed to condense from clouds at heights beneath the visible part of the atmosphere. Radio data from Earth show that the presence of ammonia molecules in the atmosphere is decreasing. This could result from the common presence of hydrogen sulfide, which interacts with ammonia, to create cloud particles of ammonium hydrosulfide. The ultraviolet spectrometer aboard Voyager detected small amounts of acetylene and ethane. These gases are byproducts of methane, which breaks down when exposed to ultraviolet light from the sun in the upper atmosphere. Uranus gives off energy that is the same as an ideal surface that absorbs all of it at negative 59.1 kelvins, which is negative 353 degrees Fahrenheit, or negative 143.4 degrees Celsius. The radiation temperature aligns with the physical temperature of the atmosphere at a pressure of about 0.4 bar. Temperature decreases as pressure falls, particularly with increasing altitude, until the 70 millibar level, where it hits around 52 Kelvin, minus 366 degrees Fahrenheit, minus 221 degrees Celsius, marking the coldest temperature in Uranus's atmosphere. As you go higher, the temperature rises again, reaching 750 Kelvin, or 990 degrees Fahrenheit, or 488 degrees Celsius, in the exosphere, which is the top layer of the atmosphere and about a Uranian radius from the center of the planet. At this altitude, the pressure is about a trillionth of a bar. We need to determine where the high temperatures in the exosphere come from, considering factors like UV absorption, electron bombardment, and the gas's inability to emit infrared wavelengths. Voyager 2 quantified the horizontal fluctuation of air temperature across two extensive altitude ranges, 60 to 200 millibars and 500 to 1,000 millibars. The fluctuation from one pole to the other in both ranges was minimal. Less than 1 Kelvin, 1.8 degrees Fahrenheit, 1 degree Celsius, even though one pole faced the sun during the flyby. The deep atmosphere's effective horizontal heat transport and substantial heat storage capacity explain the lack of global variation. Even though Uranus looks quite plain at first glance, high-contrast images taken by Voyager 2 and later Earth-based studies reveal subtle cloud bands that run parallel to the equator. Jupiter and Saturn's atmospheres are influenced by the same zonal flow. However, Jupiter and Saturn's rotational axes are tilted a little less than Uranus's, which causes very different seasonal changes in solar illumination. The rotation of the planet, instead of the distribution of absorbed sunlight, dictates the patterns of the clouds. The Coriolis force, which arises from rotation, leads to the deflection of moving materials on a rotating planet to the right or left, based on whether one is in the northern or southern hemisphere. Consequently, Uranus resembles an inverted version of Jupiter or Saturn in terms of cloud formations. The wind refers to the airflow within the atmosphere surrounding our spinning Earth. At higher latitudes on Uranus, this relative velocity is in sync with the planet's rotation. At equatorial latitudes, relative motion takes place in the opposite direction. Uranus is similar to Earth in this regard. The directions here are east and west on Earth, while the more general terms are prograde and retrograde. The winds on Uranus are much stronger than those on Earth. The wind velocity is 720 kilometers, 450 miles, per hour prograde at a latitude of 55 degrees south and 400 kilometers, 250 miles, retrograde at the equator. The winds at the move in a retrograde direction, while the winds of Jupiter and Saturn exhibit retrograde motion. No adequate theory is available to clarify these differences. Uranus does not have notable spots similar to Jupiter's persistent Great Red Spot or Neptune's Great Dark Spot, which was observed by Voyager 2 in 1989. The measurements of Uranus's wind profile taken by Voyager were based on just 4 small locations, showing a noticeable contrast of only 2 to 3% when compared to the surrounding atmosphere. The markings indicate atmospheric storms, given that the gas giants do not have solid surfaces. Uranus has the least number of storms compared to the other large planets, and the reasons for this observation require further explanation. The magnetic field and magnetosphere. Convection currents within the electrically conductive interior of Uranus, akin to those of other gas giants, generate a magnetic field. The dipole field, Akin to that of a diminutive yet powerful bar magnet, exhibits a 0.23 Gauss strength on its equatorial plane at a distance equivalent to 1 Uranian equatorial radius from the center. A standard magnetic compass indicates the counterclockwise rotating pole corresponding to Earth's north pole as the magnetic field's polarity aligns with the current geomagnetic field. The dipole axis is inclined at an angle of 58.6 degrees about the planet's rotation axis, which is markedly higher than that of Earth, 11.5 degrees, Jupiter, 9.6 degrees, and Saturn, less than 1 degree. The radius of Uranus, around 8,000 kilometers, 5,000 miles, displaces the magnetic center from the planet's core by 31%. The displacement primarily occurs along the rotational axis towards the North Pole. The magnetic field is unusual because of its tilt and shift, along with the very large size of its smaller parts. The quick attenuation of small-scale components of a field above the electrically conductive zone indicates that the field originates at shallow depths within the planet. Consequently, the interior of Uranus must exhibit electrical conductivity closer to the surface than Jupiter, Saturn, and Earth. This conclusion aligns with the established understanding of Uranus's interior composition, which predominantly consists of water, methane, and ammonia to correspond with the planet's typical density. Water and ammonia break down into cations and anions, which are electrically conductive at relatively low pressures and temperatures. Fluid dynamics within the conductive layers produce the magnetic field on Uranus. Nevertheless, these layers are shallower compared to those on Jupiter, Saturn, and Earth. Like other planets with magnetic fields, the magnetic field of Uranus deflects the solar wind, a stream of charged particles from the Sun. The planetary magnetosphere, a vast spatial zone including charged particles tethered to the magnetic field, envelopes the planet and extends downstream. On the upwind side, oriented towards the Sun, the magnetopause, the demarcation between the magnetosphere and the solar wind, is 18 Uranian radii from the planet's core. The particles confined within the Uranian magnetosphere consist of protons and electrons, suggesting that the planet's upper atmosphere provides most of the material. No evidence exists for helium, potentially sourced from the solar wind or heavier ions, which may derive from the Uranian moons. The largest moons of Uranus orbit within the magnetosphere, thereby absorbing specific trapped particles. The particles adhere to the magnetic field lines, reducing the total of trapped particles traversing a moon's orbit compared to adjacent field lines. Like Jupiter and Saturn, charged particles from the Uranian magnetosphere affect the upper atmosphere, leading to auroras. Auroral heating barely accounts for the increased temperature of Uranus's exosphere. Despite having a lower density than Jupiter, Uranus possesses a greater fraction of elements heavier than hydrogen and helium. Jupiter's superior mass increases gravitational pull by a factor of 22, leading to more self-compression than Uranus. This additional compression contributes to Jupiter's mass density. If Uranus had material proportions identical to Jupiter's, its density would have been significantly reduced. Various hypotheses suggested for the interior of Uranus postulate differing proportions of rock, silicates and metals, ices, water, methane and ammonia, and gases, mostly hydrogen and helium. Under the elevated temperatures and pressures present in the massive planets, the ices will exist as liquids. To align with the bulk density statistics, the mass of rock and ice must represent approximately 80% of Uranus's total mass, in contrast to 10% for Jupiter and 2% for a composition resembling the Sun. All models depict Uranus as a fluid planet, where the gaseous upper atmosphere progressively transitions into the liquid interior. The pressure in the planet's core is around 5 megabars, Scientists have gained deeper insight into the interior by comparing a model's response to centrifugal forces from the planet's rotation with the real measurements obtained from Voyager 2. Voyager 2 articulated this response regarding the planet's oblateness. Researchers can deduce the internal density distribution of the planet by assessing the extent of polar flattening and correlating it with the rotational velocity. Among two planets possessing identical mass and bulk density, the planet with a greater mass concentration at its center would have reduced flattening due to rotation. Before the Voyager expedition, it was not easy to choose models featuring distinct layers of rock, ice, and gas compared to those with uniformly mixed ice and gas. The significant oblateness and relatively slow rotation of Uranus, as observed by Voyager, suggests that the ice and gas are thoroughly mixed, indicating a small or non-existent rocky core. The superior fit of the mixed model of Uranus to data compared to the layered model may provide insights into the planet's genesis. The mixed model suggests that large solid objects were continuously captured by a giant planet that already possessed significant quantities of gas, rather than indicating a process where Uranus formed from a rock-ice core that later acquired gas from the solar nebula. Uranus does not emit significant surplus internal heat, unlike the other three large planets. The overall heat output is determined from the planet's measured infrared emissions, while the heat input comes from the fraction of incident sunlight that is absorbed, indicating it is not reflected back into space. The energy ratio for Uranus ranges from 1.0 to 1.14, indicating that its internal energy source provides, at most, 14% more energy than the solar input. The corresponding ratios for the other gas giants surpass 1.7. The little terrestrial planets, Mercury, Venus, Earth, and Mars, produce comparatively minimal internal heat. For instance, the heat flow from Earth's interior is about 1,000th of the solar energy it receives. It is essential to comprehend the reasons behind Uranus's minimal internal heat production compared to the other Jovian planets. Due to planetary accretion converting gravitational energy into heat, all planets must have initially been heated. Throughout the solar system's history, Earth and other smaller celestial bodies have dissipated most of their primordial heat. Nevertheless, due to their substantial mass and frigid surfaces, the large planets retain heat effectively and emit it weakly. As a result, we expect they will maintain a significant quantity of their formation heat, which continues to dissipate today. Random occurrences, such as collisions with substantial celestial bodies encountered by certain planets during their creation, along with the consequent variations in internal structure, provide one explanation for the disparities observed among the large planets, including the unusual thermal emissions of Uranus. Uranus is encircled by a minimum of 10 slender rings and has 27 identified moons. Every particle within the rings is a tiny moon in its respective orbit. The rings are closest to the planet. A few small moons orbit just beyond the rings. The largest moons orbit at a greater distance, and more small moons orbit at significantly farther distances. The orbits of the outermost group of moons are eccentric and significantly inclined to the equatorial plane of Uranus. The remaining moons in the rings are fundamentally coplanar with the equator. The 5 biggest moons of Uranus have radii ranging from around 240 to 800 kilometers. Telescopic observations from Earth resulted in the identification of all 5, with 4 discoveries made before the 20th century. From Voyager 2 identified 10 small inner moons from 1985 to 1986. Estimates indicate their radius spans from 10 to 80 kilometers, while their orbital distance from the planet varies between 49,800 and 86,000 kilometers. The innermost moon, Cordelia, orbits immediately within the outermost rings, Lambda and Epsilon. Voyager captured views of an 11th little inner moon, Perdita, adjacent to Belinda's orbit. Nonetheless, it was unrecognized in the photographs until 1999, with confirmation occurring only in 2003. In 2003, observations from Earth identified two further inner moons, Cupid, located near Belinda's orbit, and Mab, situated near Puck's orbit. All 18 aforementioned bodies exhibit normal, prograde, low inclination, and low eccentricity orbit about the planet. Commencing in 1997, Earth identified 9 little outer moons approximately within the same size parameters as the Voyager discoveries. Except for one, all these irregular satellites orbit retrogradely, possessing very elliptical orbits that are significantly inclined relative to the planet's equator. Their average distances from the planet range from 4 million to 21 million kilometers, 2.5 million to 13 million miles, 7 to 36 times the distance of the outermost known normal moon, Oberon. Uranus presumably acquired the orbits of the irregular moons after the planet's formation. The regular moons likely originated in their equatorial orbits simultaneously with the planet's formation. The 4 largest moons, Titania, Oberon, Umbriel, and Ariel, arranged by decreasing size, possess densities ranging from 1.4 to 7 grams per cubic centimeter. This range is slightly higher than the density of a theoretical object derived from cooling a solar composition combination while eliminating all gaseous components. The remaining object would consist of 60% ice and 40% rock. In contrast to these 4, Miranda, the 5th biggest moon of Uranus, is merely 1/2 the size of Ariel or Umbriel. Like the smaller moons of Saturn, Miranda possesses a 1.2 grams per cubic centimeter density, which is marginally below the solar composition value, suggesting an elevated ice-to-rock ratio. Water ice is present in the surface spectra of the 5 main moons. The moon's lower reflectivities compared to pure ice suggest that their surfaces are made up of contaminated water ice. The composition of the black region remains unknown. Nevertheless, at wavelengths distinct from water, the surface spectra seem uniformly dark, indicating a neutral gray hue devoid of iron-containing minerals, which would impart a reddish tint. One possibility is carbon, which may have originated from the moon's interiors in the issue or from the rings of Uranus. This carbon may have emitted methane gas, which dissolved into solid carbon when subjected to charged particles and solar ultraviolet radiation. 2 observations indicate that the surfaces of the main moons are permeable and have considerable insulating properties. The reflectance significantly escalates in opposition when the observer is within 2 degrees of the Sun as perceived by the planet. These purported opposing surges are typical of loosely arranged particles that obscure one another, except in this specific geometry where the viewer aligns with the illumination source, allowing direct visibility of the light reflecting from the interstitial gaps between the particles. Secondly, variations in surface temperatures correlate with solar activity throughout the day, showing negligible delay due to thermal inertia. This phenomenon is typical of porous surfaces that hinder the inward transfer of heat. Almost all knowledge regarding the unique surface features of Uranus's principal moons is derived from Voyager 2, which rapidly traversed the system in hours and captured images solely of their illuminated southern hemispheres. Oberon, particularly Umbriel, shows thick clusters of significant impact craters similar to the highlands of Earth's moon and various ancient landscapes throughout the solar system. Umbriel is the most extensively and consistently cratered of the major Uranian moons, indicating minimal tectonic reworking of its surface in the past. Titania and Ariel exhibit significantly fewer huge craters, ranging from 50 to 100 kilometers in diameter. However, they possess similar quantities in the other size categories. The extensive craters originated from the solar system's formative period over 4 billion years ago when substantial planetesimals were still present. In contrast, the smaller craters represent more contemporary occurrences, potentially including impacts from debris ejected from other moons within the Uranus system. As a result, the surfaces of Titania and Ariel need to be more recent than those of Oberon and Umbriel. The discrepancies, which lack a discernible correlation with the moon's proximities to Uranus or their dimensions, remain predominantly unaccounted for. Volcanic deposits identified on the principal moons are mainly flat, showcasing rounded edges and surface waves that suggest fluid movement. Certain deposits exhibit brightness, while others display darkness. Due to the extremely low temperatures anticipated in the outer solar system, the erupting fluid was likely a water-ammonia amalgam with a melting point significantly lower than that of pure water ice. Variations in brightness may signify differences in the composition of the erupting fluid or the surface's historical context. The rift-like canyons on the main moons indicate the extension and fracturing of their surfaces. Miranda. Miranda is the innermost and smallest of Uranus's 5 principal moons, showing the most diverse topography. In 1948, Dutch-American astronomer Gerard P. Kuiper identified Miranda in telescopic images of the Uranian system, naming it after a character from William Shakespeare's play, The Tempest. Miranda orbits Uranus once every 1.413 days on a nearly circular trajectory at an average distance of 129,800 kilometers from the planet's center. Somewhat non-spherical, it possesses a mean diameter of around 470 kilometers. The United States Voyager 2 spacecraft conducted a more detailed examination of Miranda than any other moon of Uranus, owing to its track during the 1986 flyby of Uranus, which subsequently directed it towards Neptune. Images from Voyager revealed that Miranda's surface is an unusual mosaic of meandering valleys, aligned grooves, fault scarps, and cratered peaks. The primary surface is extensively cratered. However, it is interspersed by 3 lightly cratered areas designated by astronomers as coronae, which are not geologically associated with the similarly named surface features of Venus. Curved parallel bands encircle the peripheries of these rather square zones, measuring 1 Miranda radius for each side. The boundaries where the coronas meet the cratered landscape are clear. The coronae are unique compared to any features seen in the solar system. Their origin remains uncertain, whether indicative of a diverse beginning for the moon, a massive collision that broke it apart, or a unique series of internal eruptions. Miranda's canyons are the most magnificent, with some measuring up to 80 kilometers in width and 15 kilometers in depth. The moon's volume increase, estimated at 1 to 2%, resulted in crustal rupture, except Miranda, which grew by 6%. Miranda's growth can be explained by suggesting that all the water within its interior was initially in a liquid state and then froze following the formation of its crust. When subjected to low pressure, the water would have frozen, causing it to expand and then fracture the surface. The existence of liquid water on the moon's surface at any point in its history seems unlikely. The topography variation of Miranda astonished scientists, who assumed the moon was too small, only 1/3 the diameter of its far less topographically diverse counterparts, Titania and Oberon, to have experienced the significant tectonic activity necessary to create such different terrain. We must ascertain if this activity originated from external forces, such as one or more catastrophic collisions in the moon's early history, or intrinsic factors, such as eruptions from its interior caused by historical tidal heating, akin to the phenomena observed on Jupiter's volcanically active moon Io and Ariel. Ariel is the second closest of Uranus's 5 main moons. In 1851, English astronomer William Lassell found it and named it after characters from Alexander Pope's poem, The Rape of the Lock, and William Shakespeare's play, The Tempest. Ariel orbits Uranus at an average distance of 191,240 kilometers from the planet's center, requiring 2.5 days to complete a single revolution. Ariel, akin to other significant moons of Uranus, shows synchronous rotation with its orbital period, keeping a constant orientation towards the planet and a steady forward-facing position in its orbit. The average diameter of the Moon is approximately 1,160 kilometers, 720 miles. The density is approximately 1.67 grams per cubic centimeter, 0.97 ounces per cubic inch. The U.S. Voyager 2 spacecraft obtained images during its 1986 approach to the Uranian system, showcasing scarps and extensive valley-like landforms traversing Ariel's surface. Substances that may have ascended from the Moon's interior in the past partially occupy several later formations. In certain instances, ice has spread from the valleys across vast plains, resembling glacier flows on Earth. The characteristics and the scarcity of significant impact craters indicate that Ariel possesses the most youthful surface among the principal moons of Uranus. Umbriel. Umbriel is the third closest of Uranus's 5 principal moons, possessing the darkest and most ancient surface. The English astronomer William Lassell discovered Umbriel in 1851. However, it is conceivable that William Herschel, who also found Uranus and its 2 largest moons, observed it almost 50 years prior. Umbriel was designated son of William Herschel, after a figure in Alexander Pope's poem, The Rape of the Lock. It completes an orbit around Uranus every 4,144 days at an average distance of 265,970 kilometers, 165,270 miles. Umbriel possesses a diameter of 1,170 kilometers and a density of around 1.4 grams per cubic centimeter. The photographs of Umbriel's surface came from the United States. The Voyager 2 spacecraft conducted a flyby of the Uranian system in 1986. These indicate that Umbriel is unique among Uranus's major moons due to the absence of evidence for historical tectonic activity, as evidenced by the numerous massive impact craters. The photographs captured by Voyager of the hemisphere reveal a luminous ring termed Wunda, which appears to delineate the floor of a crater with a diameter of 40 kilometers, 25 miles. Titania. Titania is Uranus's largest moon. William Herschel first observed Titania with a telescope in 1787, having discovered Uranus 6 years earlier. John Herschel, son of William, named Titania after a figure from William Shakespeare's play A Midsummer Night's Dream. Titania orbits an average distance of 435,840 kilometers from the center of Uranus, rendering it the second outermost of the planet's principal moons. Its orbital period is 8.706 days, identical to its rotational period. It is consequently in synchronous rotation, maintaining the same face oriented toward the planet and the same face directed along its orbit. The diameter measures 1,578 kilometers, and the density is around 1.71 grams per cubic centimeter. In the United States, it occurred only once in 1986. The Voyager 2 spacecraft rapidly traverses the Uranian system and closely observes Titania. Images of the spacecraft reveal a terrain characterized by numerous bright impact craters up to 50 kilometers in diameter with a scarcity of larger craters. Trenches and a deep fault line reach approximately 1,600 kilometers, 1,000 miles. These and other associated characteristics strongly indicate the presence of internal geological processes in the Moon's ancient history. Oberon. William Herschel discovered Oberon, the outermost of Uranus's 5 principal moons, and the second largest in 1787. William's son named it after a character from Shakespeare's play A Midsummer Night's Dream, similar to his choice of Titania. The average distance of Oberon from the center of Uranus is approximately 582,600 kilometers, 362,000 miles. and its orbital period is 13.46 days. Like all of Uranus's substantial moons, Oberon exhibits synchronous rotation with its orbital period, maintaining a consistent hemisphere oriented towards the planet and a fixed hemisphere advancing in its orbit. The Moon possesses a diameter of 1,522 kilometers and a density of 1.63 grams per cubic centimeter. The U.S. Voyager 2 spacecraft sent photographic photos during its 1986 flyby of the Uranian system, indicating that Oberon's surface is ancient and that certain black material, which upwelled from the Moon's subsurface, seems to have inundated several of the numerous bright craters. The ring system. We initially identified the rings of Uranus before those of any planet other than Saturn. In 1977, American astronomer James L. Elliott and his colleagues identified the ring system from Earth during a stellar occultation by Uranus 9 years before the Voyager 2 encounter, when the planet obstructed the light of a star by interposing itself between the star and Earth. They unexpectedly spotted the star temporarily dim 5 times at a significant distance above Uranus's atmosphere before and after the planet occulted it. 5 slender rings surrounded the planet, as shown by the variations in luminosity. Subsequent terrestrial observations disclosed 4 additional rings. Voyager 2 identified a 10th ring and observed evidence of more rings. The 10 rings, designated 6, 5, 4, alpha, beta, eta, gamma, delta, lambda, and epsilon, radiate from Uranus. The intricate terminology emerged from identifying new rings in areas inconsistent with the previous scheme. The rings are slender and quite opaque. The observed widths result from the integral of the radial distance multiplied by the proportion of starlight obstructed. The observation that the equivalent widths are generally fewer than the measured widths suggests that the rings are not completely opaque. The combination of the ring brightness measured in Voyager photos with the corresponding widths from occultations indicates that the ring particles reflect less than 5% of the incident sunlight. Their almost uniform reflectance spectrum suggests that the particles are mainly gray. Common soot, primarily composed of carbon, serves as the closest terrestrial analog. The origin of the carbon remains uncertain, whether it derives from the darker methane due to particle bombardment or is inherent to the ring particles. The scattering effects of Voyager's radio signal transmitted across the rings to Earth indicate that the rings predominantly comprise massive particles, objects exceeding 140 centimeters in diameter. When Voyager was positioned on the far side of the rings and directed its camera towards the Sun, the dispersion of sunlight illuminated tiny dust particles in the micrometer range. The primary rings contained a small amount of dust. The distribution of many tiny particles within the primary ring's interstitial spaces indicates that collisions result in mass loss from the rings. The drag from Uranus's extensive atmosphere and the radiation pressure from sunlight restrict the longevity of dust in orbit around the planet, causing the particles to descend to lower orbits and eventually enter the Uranian atmosphere. The computed orbital lifetimes of 1,000 years require swift and ongoing dust generation. The atmospheric drag of Uranus suggests that its current rings may be temporary. If that is the case, the rings did not originate with Uranus, and their provenance and history remain uncertain. Collisions among the densely clustered ring particles would inherently expand the ring's radial breadth. Similar to the rings of Saturn, moons that possess greater mass than the rings can impede this dispersion through shepherding. Voyager 2 discovered that the innermost 2 moons, Cordelia and Ophelia, orbit opposite sides of the epsilon ring at the precise radii necessary for shepherding. The moons might be too small to be seen in the Voyager photos, leading to the overlooked shepherds of the other rings. Minor moons might serve as reservoirs, supplying dust that leaves the ring system. William Herschel, an English astronomer, discovered Uranus while studying stars down to the 8th magnitude, approximately 5 times dimmer than those visible to the naked eye. On March 13, 1781, he discovered a peculiar, either nebulous star or possibly a comet, differentiated from the stars by its distinctly visible disk. Within months, the absence of a tail and its sluggish movement determined that the object was a planet rather than a comet or asteroid, traversing a nearly circular orbit well beyond Saturn. Observations of the new planet over the subsequent 65 years uncovered inconsistencies in its orbital motion, indicative of gravitational influences on Uranus not attributable to any other recognized planet, culminating in discovering the more remote Neptune in 1846. Herschel proposed the designation Georgium Sidus, Latin Georgian planet, for his new discovery in honor of his patron, King George III of England, although the French preferred Herschel. The convention of naming planets after deities from Greek and Roman mythology culminated in the designation of Uranus, the progenitor of Saturn, who is, in turn, the progenitor of Jupiter. The initial missions of the twin Voyager 1 and 2 spacecraft were limited to flybys of Jupiter and Saturn. However, the launch schedule of Voyager 2 permitted a trajectory alteration that enabled it to be redirected to Uranus and Neptune for an extended mission, which it successfully executed. On January 24, 1986, Voyager 2 traversed the Uranian system after over 8 years in space. The instruments of Voyager 2 precisely measured the masses and radii of Uranus and its principal moons, identified the planet's magnetic field, assessed its strength and orientation, and evaluated the inner rotation rate of the planet. Over 8,000 images of the Uranian system unveiled for the first time the atmospheric weather patterns of the planet and the surface features of its moons. Besides Voyager's findings of new moons, a ring and dust bands between the rings, it provided insights into ring structure at sizes that cannot be attained from Earth. Nevertheless, despite these accomplishments, Voyager generated numerous unresolved inquiries that could only be clarified through an additional spacecraft voyage or significant advancements in terrestrial observatory technology. Since 2009, no missions to Uranus have been planned. Neptune. Neptune is the third most massive planet in the solar system and the 8th planet from the Sun. The naked eye cannot perceive it because of its great distance from Earth. However, through a small telescope, it manifests as a little, faint, blue-green disk. Poseidon, the Greek deity and son of Titan Cronus, who is known as the Roman god Saturn, is the brother of Zeus, the Roman god Jupiter, and the source of Neptune's name. Utilizing a telescope, scientists identified Neptune as the second planet. The discovery in 1846 exemplified a notable integration of rigorous Newtonian physics, with a reliance on a numerological framework that subsequently was demonstrated to be scientifically invalid. Neptune's orbit is nearly round, resulting in minimal variation in its distance from the Sun throughout its 164-year revolution period. Despite Pluto's mean distance from the Sun being larger than Neptune's, its very eccentric orbit results in Pluto being closer to the Sun than Neptune for about 20 years of each revolution. Neptune is over 4 times larger than Earth, but slightly smaller than Uranus, making it the smallest in diameter among the 4 large, or Jovian, planets. Nonetheless, it possesses greater mass than Uranus, with a density around 25% superior. Like the other gas giants, Neptune is predominantly composed of hydrogen, helium, water, and many volatile substances, along with rocky material, and lacks a solid surface. Neptune receives less than 50% of Uranus's sunlight. Nonetheless, geothermal heat emanating from its interior renders Neptune somewhat warmer than Uranus. The heat released may contribute to the storminess of Neptune's atmosphere, which displays the highest wind speeds observed on any planet in the solar system. Before the passage of the Voyager 2 spacecraft in 1989, only 2 of Neptune's 13 moons were identified, and its ring system was not verified until Voyager's exploration. Like Uranus, a single spacecraft encounter provided scientists with most of their knowledge about Neptune, including its rotation period and the characteristics of its magnetic field and magnetosphere. Recent advancements in Earth-based observational technology have yielded new insights into Neptune's orbital period of 163.72 years indicates that by mid-2010, it will have completed a single revolution around the Sun since its discovery in September 1846. As a result, astronomers anticipate refining their calculations of its orbital dimensions and configuration during the 21st century. The interaction between Voyager 2 and Neptune resulted in a marginal augmentation of the planet's estimated average distance from the Sun, presently calculated at 4,498,250,000 kilometers, 2,795,083,000 miles. The orbital eccentricity of 0.086 is the second lowest among the planets, surpassed only by Venus's orbit in circularity. Neptune's rotation axis is inclined at 29.6 degrees relative to its orbital plane, exceeding Earth's tilt of 23.4 degrees. Like Earth, Neptune's axial tilt results in seasons, and due to the round nature of its orbit, the seasons, and those of its moons, are of almost equal duration, each lasting nearly 41 years. Voyager 2 determined Neptune's rotation period by identifying radio bursts linked to the planet's magnetic field, exhibiting 16 points per hour. We deduced this value to signify the rotation period within the planet's interior, where the magnetic field is generated. The equatorial diameter of Neptune, measured at the 1 bar pressure level, equivalent to Earth's sea-level atmospheric pressure, is 49,528 kilometers, 30,775 miles, approximately 3% less than that of Uranus. Neptune's rapid rotation causes the poles to flatten, leading to a polar diameter of 848 kilometers less than its equatorial diameter. Despite Neptune having a slightly smaller volume than Uranus due to its higher density, 1.64 grams per cubic centimeter, compared to around 1.3 for Uranus, Neptune's mass is 18% more. The atmosphere. Like other gas giants, Neptune's outer atmosphere predominantly comprises hydrogen and helium. At the 1 bar pressure level in the atmosphere, these two gases account for approximately 98% of atmospheric molecules. The majority of the residual molecules are composed of methane gas. Hydrogen and helium are nearly undetectable. However, methane shows considerable absorption of red light. Sunlight reflects off Neptune's clouds, resulting in the atmosphere losing many red hues and acquiring a bluish tint. The blue-green hue of Uranus is attributed to atmospheric methane, while Neptune displays a more vibrant and brighter blue, possibly due to an undiscovered atmospheric gas. The temperature of Neptune's atmosphere varies with elevation. Neptune is about 50% farther from the Sun than Uranus, resulting in it receiving less than half the sunlight of Uranus. However, the effective temperatures of these two gas giants are almost the same. Uranus and Neptune reflect, and consequently absorb, about the same fraction of the sunlight that reaches them. Due to processes that are not entirely comprehended, Neptune radiates more than 2 times the energy it absorbs from the Sun. The interior of Neptune produces additional energy. In contrast, Uranus has less energy loss from its interior. At the 1 bar reference level, the average temperature of Neptune's atmosphere is approximately 74 Kelvin, negative 326 degrees Fahrenheit, negative 199 degrees Celsius. Atmospheric temperatures are a few degrees higher near the equator and poles compared to mid-latitudes. This signifies that air currents ascend around mid-latitudes and decrease near the equator and poles. This vertical flow can reach considerable altitudes inside the atmosphere. A more vertically restricted horizontal wind system is present at the cloud tops. Like other gas giants, Neptune's atmospheric circulation exhibits zonal flow, characterized by winds predominantly moving along lines of constant latitude, east-west, and maintaining relative stability throughout time. Winds on Neptune vary from approximately 100 meters per second, 360 kilometers, 220 miles per hour, in an easterly direction, prograde, aligned with the planet's rotation, at latitude 70 degrees south to as much as 700 meters per second, 2,500 kilometers per hour, 120 kilometers, 1,570 miles per hour, in a westerly direction, retrograde, contrary to the planet's rotation, 20 degrees south. The intense winds and considerable internal heat may account for the turbulence detected in Neptune's visible atmosphere by Voyager 2. Two prominent black ovals were distinctly observable in Voyager photos of Neptune's southern hemisphere. The largest, referred to as the Great Dark Spot, due to its resemblance in latitude and shape to Jupiter's Great Red Spot, is comparable in size to our planet. We recorded the highest wind velocities adjacent to this storm system. Telescopes on Earth have monitored Jupiter's Great Red Spot for more than 300 years. Scientists anticipated Neptune's Great Dark Spot would endure for a similar duration. Scientists were consequently astonished by its absence in photographs of Neptune captured by the Earth-orbiting Hubble Space Telescope in 1991, hardly 2 years post-Voyager visit, as they were by the emergence of a similar black patch in Neptune's northern hemisphere in 1994. The luminous cloud formations shown in the Voyager photos are notably more fleeting. They could be methane ice clouds formed by vigorous upward movements of methane gas pockets to elevated, colder altitudes in the atmosphere, where the gas condenses into ice crystals. Neptune is the only large planet showing cloud shadows created by highly dispersed clouds on a lower, more uniform cloud layer. The primary cloud layer, possibly comprising ice crystals of ammonia or hydrogen sulfide, is 50 to 100 kilometers above the upper clouds, presumably formed of methane ice crystals. Like other gas giants, Voyager's remote sensing equipment detects deeper cloud layers on Neptune, where the gas composition predominantly comprises sulfur and nitrogen molecules. We anticipate the formation of water ice clouds at depths in Neptune's atmosphere where the pressure exceeds 100 bars. The magnetic field and magnetosphere. Like other planets in the solar system, Neptune has an internally generated magnetic field, initially identified in 1989 by Voyager 2. Neptune's magnetic field, akin to Earth's, resembles a dipole, similar to a bar magnet, although its polarity is fundamentally opposite to Earth's current field. A magnetic compass on Neptune would indicate south instead of north. Electric currents in Earth's liquid iron core produce its magnetic field, whereas the outer cores of liquid metallic hydrogen in Jupiter and Saturn may similarly generate their magnetic fields. The magnetic fields of Earth, Jupiter, and Saturn are mainly concentrated within the planets and aligned within about 12 degrees of their rotational axes. In contrast, Uranus and Neptune possess magnetic fields inclined at almost 59 degrees and 47 degrees from their rotational axes. Moreover, the fields exhibit a lack of internal centering. The offset of Uranus's magnetic field is 31% of the planet's radius, but Neptune's magnetic field, offset by 55%, is situated in an internal region nearer to the cloud tops than the planetary core. Researchers hypothesize that phenomena within the top strata of planetary innards may produce the unusual arrangements of Uranus and Neptune's magnetic fields. The magnetic fields of Neptune and other planets resemble apples. with the stem and opposite end aligned with the magnetic poles. The solar wind, a flow of electrically charged particles from the sun, alters the planet's regular shape by compressing it on the sunward side and elongating it into a tail directed away from the sun. Charged particles, primarily protons and electrons, are confined within the magnetic field. The magnetic field of Neptune and its charged particles predominate in the area of space referred to as its magnetosphere. The notable tilt of Neptune's magnetic field consistently guides the trapped particles in the magnetosphere along the paths of the moons and rings. The moons and ring material may absorb many particles, significantly depleting the magnetosphere of its charged particle concentration. Neptune's magnetosphere contains a lower density of protons and electrons per unit volume than any other large planet. In proximity to the magnetic poles, charged particles within the magnetosphere can traverse magnetic field lines into the atmosphere. Their collision with gases induces fluorescence in those gases, producing classical, though weak, auroras. Despite having a mean density below 30% of Earth's, Neptune is the most dense among the large planets. This indicates that melting ice and molten rock make up a larger portion of Neptune's interior than other giant planets. The distribution of these denser elements and compounds requires further clarification. Data from Voyager 2 indicate that Neptune is improbable to possess a unique inner core of molten rock components encased by an outer core of liquefied ices composed of methane, ammonia, and water. Based on the layered inner model, Voyager's measured rotation period of 16.1 hours was approximately 1 hour longer than anticipated. Researchers have determined that, rather than centrally condensing, the denser chemicals and elements may distribute nearly equally throughout the interior. In this regard, Neptune resembles Uranus more closely than the larger gas giants, Jupiter and Saturn. Neptune may not be hotter at its core than Uranus, even though the planet's interior significantly influences its overall heat budget. Many layers in the deep Uranian atmosphere may protect the interior, confining the radiation that more easily dissipates from Neptune within the planet. Photographs of Uranus taken from Earth as it nears an equinox and the sun progressively illuminates the equatorial regions indicate a more dynamic atmosphere. This suggests that the unique atmospheric phenomena on Uranus and Neptune are more influenced by solar radiation than the relative amounts of heat emanating from their interiors. Moons and rings of Neptune. Neptune possesses a minimum of 13 moons and 6 identified thin rings. Every particle comprising the rings might be regarded as a small moon in its respective orbit. The 4 moons nearest to the planet orbit within the ring system, where some may exert gravitational influence on the ring particles, preventing their dispersion. Before Voyager 2's encounter, Neptune's only identified moons were Triton, visually detected through a telescope in October 1846 by English astronomer William Lassell, shortly after Neptune's discovery, and Nereid, which was identified in telescopic photographs over a century later in 1949 by American astronomer Gerard Kuiper. In 1989, Voyager's observations revealed 6 previously undiscovered moons in Neptune's system. All are situated at less than 1/2 of Triton's distance from Neptune and are classified as regular moons, meaning they circle in a prograde direction along roughly circular paths aligned with Neptune's equatorial plane. These moons are likely synchronous rotators, showing the same rotational and orbital periods. Observations from Earth in 2002 to 2003 identified 5 new diminutive moons, each estimated to have a radius of approximately 15 to 30 kilometers. These are irregular, possessing highly eccentric orbits inclined at significant angles to the planet's equator. 3 orbit in a retrograde manner. Their average distances from Neptune range from 15 million to 48 million kilometers, much beyond the orbit of Nereid. Greek mythology connects the moons of Neptune to Poseidon, the Roman god Neptune, or water. Of Voyager's 6 discoveries, all but Proteus orbit Neptune in a duration shorter than the planet's rotation period. Consequently, an observer near Neptune's cloud tops would witness these 5 celestial bodies ascending in the west and descending in the east. Voyager closely examined 2 of its findings, Proteus and Larissa, enabling the detection of their size and approximate shape. Both bodies exhibit unusual shapes and display notably cratered surfaces. We approximate the dimensions of the remaining 4 by analyzing distant photos and their luminosities, presuming they reflect around 7% of the light from Proteus and Larissa. The next 5 moons are far smaller, each possessing a mean radius of under 100 kilometers. The following text offers more detailed profiles of Neptune's 3 largest moons, Triton, Proteus, and Nereid. Triton. The unusual orbital characteristics of Triton, Neptune's largest moon, suggest that it came from a different solar system area before being captured by Neptune. Triton derives its name from a merman in Greek mythology, recognized as the offspring of the sea deity Poseidon, equivalent to the Roman god Neptune. Triton is distinctive among the solar system's large moons due to its retrograde orbit, contrary to Neptune's rotation. The average orbital distance is approximately 354,800 kilometers from the Earth. Triton's orbital inclination, exceeding 157 degrees relative to Neptune's equator, is atypical for a sizable moon. The orbits of the other significant moons in the solar system are inclined by less than 5 degrees relative to their planet's equator. Triton completes a single axial rotation every 5.87 days, coinciding with its orbital period around Neptune. The synchronous rotation causes the moon to consistently present the same face to Neptune while maintaining this orientation throughout its orbit. Triton's seasons, similar to Neptune's, last about 41 years, making up 1/4 of Neptune's orbital period. Triton's orbital inclination, coupled with its axial tilt of 30 degrees about Neptune's orbit, and the moon's poles periodically orienting toward the sun, akin to the behavior observed in Uranus. Little information was available regarding Triton until 1989 when the United States. The Voyager 2 probe approached within 40,000 kilometers of it. As Voyager estimated, Triton has a diameter of approximately 2,706 kilometers, nearly equivalent to Earth's moon. Before Voyager, estimations of Triton's size from Earth relied on an inaccurately elevated mass assessment and a presumption of minimal surface reflection. Triton's mass is now understood to be a mere fraction of the previously recognized amount, and its surface is icy and highly reflective, in contrast to the moon's dark surface, which is devoid of water and other volatile substances, except for water ice found in the floors of craters at its poles. The low mass of Triton is likely a result of an interior mainly made up of water ice surrounding a denser, rocky core. Nonetheless, its average density of 2.06 grams per cubic centimeter exceeds that recorded for any satellites of Saturn or Uranus, and is only surpassed among large satellites by the Moon and Jupiter's Io and Europa. Triton shows similarities in size, mass, and surface composition to the dwarf planet Pluto. Triton's significantly tilted retrograde orbit suggests it is a captured entity, perhaps emerging as an independent icy planetesimal in the outer solar system, similar to Pluto. At a certain juncture in Neptune's primordial history, Triton's solar orbit may have brought it too near to the colossal planet. The gas drag in Neptune's expansive atmosphere, or a collision with an existing moon of Neptune, decelerated Triton sufficiently to establish it in an elongated, retrograde, and highly inclined orbit. Tidal interactions between Triton and Neptune, cyclical deformations in one celestial body due to the gravitational pull of the other, would ultimately have altered Triton's orbit around Neptune into a circular trajectory. Triton's capture and orbital circularization would have greatly disturbed any pre-existing moon system formed with Neptune from a disk of protoplanetary material. We have not dismissed the notion that Nereid is a captured object. Nonetheless, this procedure may have resulted in Nereid's eccentric orbit. The molten Triton would have either absorbed the moons in closer orbit to Neptune, expelled them from the Neptunian system, or impacted Neptune directly. Even the moons in closer orbit to Neptune would have experienced significant disruption. The present orbits of Nereid and Proteus likely diverge significantly from their original trajectories, suggesting that these moons may merely be remnants of the primordial bodies that coalesced with Neptune. The subsequent bombardment by debris orbiting Neptune and meteoroids from interplanetary space may have further modified their sizes, shapes, and orbits. Methane and nitrogen ice cover Triton's visible surface. Spectroscopic investigations from Earth indicate the presence of trace quantities of carbon monoxide and carbon dioxide ice. Voyager recorded the surface temperature as 38 Kelvin, equivalent to negative 390 degrees Fahrenheit, negative 235 degrees Celsius. Nevertheless, sufficient frozen nitrogen sublimes to generate a tenuous atmosphere with a pressure of less than 200 thousandths of a bar at the surface. During the Voyager flyby, a polar ice cap, apparently consisting of nitrogen ice deposited the previous winter, encompassed most of Triton's southern hemisphere. Triton was approximately halfway through its 41-year southern spring at that time. Equatorward of the polar cap, the terrain resembled a cantaloupe rind, characterized by dimples interspersed with a network of fractures. Many darker streaks within the polar cap region indicate the presence of surface winds. At least two of the streaks, perhaps many, originate from active geyser-like plumes observed during the Voyager 2 flyby. Ventilation in the soup-adjacent ice permits the release of nitrogen gas, transporting suspended dust particles to altitudes of approximately 8 kilometers, from whence they disperse up to 150 kilometers downwind. Although we still need to understand the energy sources and mechanisms propelling these plumes, their inclination towards latitudes irradiated vertically by the sun suggests that incident sunlight plays a vital role. On the Neptune-facing side of Triton, near the equator, there are at least two, and perhaps numerous, frozen lake-like formations with terraced peripheries. The terracing results from many melting epochs, with each subsequent melt affecting a smaller ice area. Certain terrace cliffs ascend beyond 1 kilometer in height. Despite Triton's low surface temperature, nitrogen or methane ice requires more strength to support constructions of that height without succumbing to slumping. Despite the absence of concrete evidence in Triton's spectra, scientists hypothesize that water ice is the foundational element in these formations, which exhibit a more rock-like consistency at low temperatures. A tiny layer of nitrogen or methane ice might hide the water ice's spectral signature. The transition from capture to circular orbit may have exceeded 1 billion years, during which the significant tidal deformations endured by Triton likely resulted in the melting of its entire interior. The molten mass would have experienced differentiation, causing denser materials to descend into the core while more volatile substances ascended to the surface. Scientists argue that Triton's surface cooled more rapidly than its innards, forming a dense outer layer predominantly of water ice. Proteus is Neptune's second-largest moon, named for the prophetic, shape-shifting elder of the sea in Greek mythology. It was among the moons identified by Voyager 2 in 1989. Proteus has a mean radius of around 208 kilometers, making it slightly larger than Nereid, which has a mean radius of about 170 kilometers. Nevertheless, due to Proteus's proximity to Neptune, terrestrial scientists could not discern it amidst the planet's brightness. Nereid is the third-largest moon identified in Neptune. In Greek mythology, it is named after the numerous daughters of the sea deity Nereus, known as Nereids. Nereid possesses a diameter of around 340 kilometers. With a period exceeding 360 days and an inclination greater than 7 degrees relative to the planet's equator, Nereid orbits Neptune with the most eccentric trajectory of any known moon. Its average distance from Neptune is 5,513,400 kilometers, approximately 15 times greater than the nearest known moon, Triton. Nereid is exceptionally dim, rendering studies with even the most powerful Earth-based telescopes somewhat challenging. As a result, the available information is limited. However, the United States provides reflectivity data. In 1989, the Voyager 2 space probe indicated a surface composition of ice and silicates. The concept posits that Neptune's gravitational influence ensnared Triton, a sibling of Nereid, whose protracted settling-in period, lasting 1 billion years, significantly disturbed Neptune's primordial moon system. Nereid may be a captured body originating in a different solar system region. Voyager did not detect Nereid at close proximity. However, data from the probe suggests that it possesses a nearly spherical shape. Voyager observed no notable changes in brightness throughout Nereid's rotation. The spacecraft could not determine a rotation period. However, the Moon's elliptical orbit makes synchronous rotation unlikely, indicating that its rotation and orbital periods are unequal. Evidence of one or more rings around Neptune emerged in the mid-1980s, when stellar occultation investigations from Earth sometimes revealed a transient decrease in a star's brightness immediately before or after the planet obscured it. Scientists determined that the rings detected do not fully encircle Neptune. Rather, they manifest as partial rings or ring arcs, as evidenced by the reported dips in certain studies, which were never symmetrical on both sides of the planet. Images from Voyager 2, however, disclosed a system of 6 rings, each completely around Neptune. Voyager 2 revealed the alleged arcs as luminous areas in the outermost ring, atoms, characterized by a notable density of ring particles. While rings also surround the other 3 gas giants, none exhibit the remarkable clumpiness characteristic of atoms. The 5 additional recognized rings of Neptune, Gale, Leverrier, Lassell, Arago, and Galatea, arranged by increasing distance from the planet, do not exhibit the density non-uniformity characteristic of atoms. Leverrier, with a radial diameter of approximately 110 kilometers, closely matches the non-arc areas of atoms. Similar to the relationship between the moon Galatea and the ring atoms, the moon Despina orbits Neptune within the ring Leverrier. Each moon may gravitationally resist particles at the inner boundary of its corresponding ring, functioning as a shepherd moon to prevent the inward dispersion of ring material. Gale, the innermost ring, is significantly wider and dimmer than atoms and Leverrier, likely due to the absence of a nearby moon that can offer a considerable shepherding influence. A subtle plateau of ring material, referred to as Lassell, extends outward from Leverrier to around the midpoint of atoms. Arago is the small, glowing region surrounding the edge of Lassell. Galatea often denotes a fragile ring of material that spans the moon's orbit. The scattering effects on Voyager's radio signal did not identify Neptune's rings, indicating a near-complete absence of particles of centimeter size or larger. Sunlight illuminating the rings in Voyager photos indicated that they were predominantly dust-sized particles, which scatter light more efficiently forward than back toward the Sun and Earth. The chemical composition remains unknown. However, similar to the rings of Uranus, the surfaces of Neptune's ring particles may consist of radiation-altered methane ice and possibly the particles themselves. We can extrapolate the presumed youthfulness of Adams's ring arcs and the accompanying arguments to Neptune's rings. The present rings are slender, and researchers have struggled to clarify how the paths of the observed moons can sufficiently limit the natural radial dispersion of the rings. This has prompted speculation that Neptune's current rings may be far younger than the planet, possibly less than 1 million years old. The current ring system may significantly differ from 1 million years prior. The forthcoming spacecraft visiting Neptune's rings may encounter a more advanced system than that which Voyager 2 captured in 1989. The only large planet that requires a telescope for observation is Neptune. With an apparent magnitude of 7.8, it is roughly 1/5 as luminous as the dimmest stars observable without optical help. As a result, Neptune's sightings happened after the introduction of telescopes. Galileo began using a telescope to observe the cosmos. On December 20th, 2012, he produced his initial sketches, indicating that he observed Neptune near Jupiter, but still needed to identify it as a planet. Before the discovery of Uranus by the English astronomer William Herschel in 1781, scientists and philosophers believed that the solar system had only 6 planets: Earth and the 5 planets observable in the sky since antiquity. The discovery of a 7th planet prompted astronomers and others to hypothesize the presence of additional planetary entities. The mathematical phenomenon known as Bode's law provided further motivation. Several astronomers were astonished by how effectively Bode's rule clarified the distances between Ceres and Uranus. They came up with the name Ophion for the solid planet that the law said must exist beyond Uranus at 38.8 astronomical units. Aside from this scientifically unfounded assertion, investigations of Uranus produced evidence for the presence of another planet. Newton's equations of motion and the gravitational influences of the Sun and other planets failed to forecast the trajectory of Uranus. Moreover, more than 20 documented pre-discovery sightings of Uranus, originating from 1690, exhibited inconsistencies with the computed locations of Uranus for each observation. The gravitational pull of an undiscovered planet is affecting the orbit of Uranus. In 1843, British mathematician John Couch Adams commenced an earnest investigation to ascertain the whereabouts of a more remote planet that would explain Uranus's anomalous movements. Adams conveyed his findings to the Astronomer Royal, George B. Airy, at the Greenwich Observatory, but they needed more precision to initiate a sufficiently focused search for the new planet. Urbain Jean-Joseph Leverrier of France, oblivious to Adams's endeavors in Britain, initiated a comparable investigation in 1845. By mid-1846, English astronomer John Herschel, son of William Herschel, articulated his belief that the ongoing mathematical investigations could potentially result in finding a new planet. Convinced by Herschel's reasoning, Airy recommended a search based on Adams's estimates to James Challis at the Cambridge Observatory. Challis began systematically examining a vast sky area next to Adams's expected location. Challis's lack of detailed maps of the faint stars in the expected area of the new planet made the search lengthy and difficult. He would create charts of the stars he viewed and compare them with the same spot several nights later to ascertain if any had shifted. Leverrier faced challenges in persuading astronomers in his nation that conducting a telescopic survey of the region he identified for the new planet was worthwhile. On September 23, 1846, he conveyed his findings to the German astronomer Johann Gottfried Galle at the Berlin Observatory. Galle and his helper Heinrich Louis d'Arrest utilized meticulously crafted star maps to facilitate the search for new asteroids. Galle and d'Arrest recognized Neptune as an unknown celestial body that evening and confirmed its movement about the background stars the following night. While Galle and d'Arrest were the initial observers of Neptune in the night sky, the credit for its discovery probably resides with Leverrier, due to his calculations regarding Neptune's trajectory. Initially, the French endeavored to designate Leverrier as the exclusive discoverer of the new planet and proposed that it be named in his honor. The acknowledged contribution of Adams and the widespread reluctance to name a major planet after a contemporary individual negatively impacted the proposal's acceptance beyond France. Adams and Leverrier ultimately garnered recognition for the discovery of Neptune, although it now appears that Adams's role was less significant than previously assumed. It is fitting that the traditional practice of naming planets after figures from ancient mythology ultimately prevailed. The discovery of Neptune conclusively refuted Bode's law. It revealed that Neptune's distance from the Sun was 31 astronomical units, considerably less than the expected 38.8 astronomical units. The inconsistency and lack of scientific rationale for the law's function undermined its credibility. The great distance of Neptune from Earth and the Sun significantly hindered observations of the planet from Earth before Voyager 2's flyby. The average orbital radius of 30.1 astronomical units indicates that the sunlight reaching its moons and upper atmosphere is just 0.1% as intense as Earth's. Before the Voyager mission, telescopic observations of Neptune through the entirety of Earth's atmosphere could not discern features smaller than 1/10 of Neptune's diameter, even under optimal viewing conditions. Most observations concentrated on determining Neptune's dimensions, mass, density, and orbital characteristics, and exploring its moons. In the early 21st century, specialized interferometric techniques consistently enhanced the spatial resolution of distant objects by factors of 10 to 100 compared to previous surface-based observations. Astronomers intermittently documented visible features in Neptune's atmosphere, but it was in the 1980s that they employed high-resolution infrared charge-coupled device, CCD cameras, to conduct these observations consistently, enabling them to ascertain an approximate rotation period for Neptune. Spectroscopic measurements conducted from Earth indicated the existence of hydrogen and methane in the planet's atmosphere. Compared with the other gas giants, we anticipated the existence of helium. And optical analyses indicated that Neptune has an interior heat source. By the middle of the 1990s, the fully operational Hubble Space Telescope, HST, facilitated the acquisition of photos and data regarding Neptune, circumventing the filtering and distorting influences of Earth's atmosphere. The Spitzer Space Telescope, orbiting in infrared, successfully captured images of Neptune with a resolution significantly superior to those obtainable from Earth's surface in the 1980s. Astronomers have devised methods to lessen the impact of air distortion in observations made from Earth. The most effective of them, termed adaptive optics, continuously analyzes data from infrared star pictures and promptly adjusts the telescope mirror's shape to rectify distortion. As a result, large Earth-based telescopes consistently achieve resolutions better than the Hubble Space Telescopes. Images of Neptune captured using adaptive optics facilitate investigations of this remote planet at resolutions nearing those achieved during the Voyager 2 mission. Voyager 2 is the sole spacecraft that has interacted with the Neptunian system. Launched in 1977, Voyager 2 and its counterpart Voyager 1 initially planned to explore only Jupiter and Saturn. However, the timing of Voyager 2's launch allowed for a trajectory adjustment, utilizing a gravity assist from Saturn, enabling extended missions to Uranus and Neptune. Voyager 2 traversed Neptune and its moons from August 24 to 25, 1989, conducting nearly continuous system observations from June to October. The measurement of the planet's radius and internal rotation rate, along with the detection of its magnetic field, revealed that it is significantly inclined and displaces the planet's rotational axis. We have verified the presence of rings on Neptune and discovered 6 new moons. Voyager's photographs of Neptune revealed the most intense atmospheric winds in the solar system and numerous large-scale storms, one of which is comparable in size to Earth. As Neptune was Voyager 2's final planetary destination, mission scientists took the risk of positioning the spacecraft closer to it than to any other planet throughout the trip. Voyager traveled approximately 5,000 kilometers over Neptune's northern pole. Several hours later, it approached within 40,000 kilometers of Triton, enabling the acquisition of high-resolution photos of the Moon's diverse surface and accurate measurements of its radius and surface temperature. As of 2009, there are no proposed missions to Neptune, Pluto, the Kuiper Belt, and beyond. Neptune is the 9th planet in the solar system. Beyond Neptune lies not vacant space, but many peculiar ice-bound celestial bodies, including the Kuiper Belt and its most prominent constituent, the dwarf planet Pluto. Historically, scientists regarded Pluto as the most distant and smallest planet. In 1930, scientists regarded Pluto as the most recently identified planet. In August 2006, the scientific community mandated the International Astronomical Union to exclude Pluto from the planetary roster and designate it as a dwarf planet. The alteration signifies astronomers' acknowledgement that Pluto is a significant part of the Kuiper Belt, a collection of icy and rocky remnants from the solar system's beginning, orbiting the Sun beyond Neptune's path. Pluto is not visible to the human eye in the night sky. Nonetheless, its largest moon, Charon, is sufficiently comparable to the dwarf planet, leading to the prevalent designation of the two entities as a double system. Pluto, named after the Roman deity of the underworld, with Hades as its Greek counterpart, lies at such a distance that sunlight, traveling at approximately 300,000 kilometers, 186,000 miles per second, takes over 5 hours to reach. A person on Pluto's surface would perceive the Sun as an exceptionally luminous star in the dark sky, delivering approximately 1/16 of the sunlight that reaches Earth. Pluto's surface temperature is so low that ordinary gases such as nitrogen and carbon monoxide exist as ice. Due to Pluto's distance and small size, the most advanced telescopes on Earth and in orbit have been unable to discern much detail on its surface. Determining fundamental data such as Pluto's radius and mass has been difficult. The discovery of Charon in the late 1970s has significantly contributed to our understanding of Pluto. Despite the absence of previous spacecraft visits to Pluto, the U.S. probe New Horizons launched from Earth in 2006 and plans to reach the Pluto-Charon system in July 2015. Only detailed robotic observations can address many critical inquiries regarding Pluto and its surroundings. Pluto's average distance from the Sun, around 5.9 billion kilometers, results in an orbit exceeding Neptune's outermost planet. Compared to the other planets, Pluto's orbit shows several unique characteristics. The orbit of Pluto is more extended or eccentric than any other planetary orbit, and it exhibits a greater inclination of 17 degrees 1 minute to the ecliptic, the plane of Earth's orbit where most planetary orbits lie. Pluto's orbit around the Sun ranges from 29.7 astronomical units at perihelion to 49.5 astronomical units at aphelion. Due to Neptune's almost circular orbit of 30.1 astronomical units, Pluto is closer to the Sun for a brief period during each cycle than Neptune. However, the two celestial bodies will never intersect because Pluto is in a stabilizing 3:2 resonance with Neptune. Specifically, it completes 2 cycles around the Sun in the same duration Neptune completes 3. This gravitational contact influences their orbits, preventing them from approaching closer than 17 astronomical units. Pluto last attained perihelion in 1989. For approximately a decade preceding and following that event, Neptune was further from the Sun than Pluto. Observations of Earth have determined Pluto's rotation period, or sidereal day, to be 6.383 Earth days. Among the celestial bodies, only Mercury, with a rotation period of about 59 days, and Venus, with a rotation period of 243 days, exhibit slower rotation. Pluto tilts its rotational axis at an angle of 120 degrees to the perpendicular of its orbital plane, positioning its north pole 30 degrees below this plane. On the other hand, Earth's north polar axis tilts at a perpendicular angle of 23.5 degrees, placing it above its orbital plane. Pluto rotates almost horizontally retrogradely. An observer on its surface would witness the sun rising in the west and setting in the east. In comparison to the planets, Pluto has unusual physical characteristics. Pluto's radius is less than 50% of Mercury's. It is approximately 2/3 the size of Earth's moon. Compared to the outer planets, such as the massive Jupiter, Saturn, Uranus, and Neptune, Pluto's radius is remarkably small. By integrating these attributes with our knowledge of its density and composition, Pluto appears to exhibit greater resemblance to the large ice moons of the outer planets than to any of the planets themselves. Neptune's moon, Triton, is its nearest counterpart, indicating a potentially similar origin for both celestial bodies. Scientists gained confidence in the presence of an atmosphere when they detected methane ice on Pluto's surface in the 1970s, but they delayed direct observation until the following decade. In 1988, Earth witnessed Pluto occulting a star, resulting in the discovery of its atmosphere. The star's luminosity gradually decreased before its obscuration by Pluto, indicating the presence of a thin, notably expanded atmosphere. Minor temperature fluctuations significantly influence Pluto's atmosphere, composed of vapors in equilibrium with their ices, and can substantially alter its gas volume. In the years near Pluto's perihelion in 1989, when its temperature was marginally warmer than usual, a greater volume of its frozen gases sublimated, resulting in an atmosphere at or near its maximum density, providing an advantageous opportunity for study. Astronomers estimate the surface pressure between a couple and several tens of microbars. Pluto's atmosphere might be undetectable at aphelion due to minimal solar exposure. Observations conducted during occultations do not yield direct data regarding atmospheric composition. However, they facilitate the calculation of the ratio of mean molecular weight to temperature. Based on acceptable assumptions on atmospheric temperature, scientists have determined that the mean molecular weight of each particle, specifically each atom or molecule, in Pluto's atmosphere is approximately 25 atomic mass units. This indicates that substantial quantities of gases denser than methane, with a molecular weight of 16, must also exist. Identifying nitrogen ice on the surface, which exhibits greater volatility than methane ice, suggests that molecular nitrogen is the predominant component with a molecular weight of 28. Nitrogen is the primary component of the atmospheres of Triton, Titan, and Earth. While continuous Earth-based observations will enhance understanding of Pluto's atmosphere and other characteristics, significant new revelations would necessitate a direct encounter with a mission. Researchers examined the United States. The New Horizons spacecraft mission, initiated in 2006, aims to explore Pluto, Charon, and the outer solar system to gather essential data. The mission design anticipated a 9-year voyage to the Pluto-Charon system, succeeded by a 150-day flyby to investigate the surfaces, atmospheres, innards, and spatial environment of the two celestial planets. Observations of Pluto indicate that its hue is somewhat reddish, yet somewhat less so than that of Mars or Jupiter's moon Io. Therefore, the observed brightness variations resulting from its rotation confirm that Pluto's surface cannot consist solely of pure ice. Its mean reflectivity, or albedo, is 0.5, indicating it reflects 55% of the incident light, in contrast to 0.1 for the Moon and 0.8 for Triton. Initial rudimentary infrared spectroscopic measurements indicate Pluto's unusually bright southern polar area. Scientists consider the variance in Pluto's surface remarkable since, aside from Saturn's enigmatic moon, Iapetus, all other frozen worlds in the outer solar system display significantly more uniform surfaces. Brightness maps created from observations with the Hubble Space Telescope as it orbited around the Earth reveal some of this diversity. However, only visiting spacecraft can provide the spatial resolution to connect brightness with surface composition or topography. Pluto-Charon eclipses have allowed astronomers to determine the masses and radii of both celestial bodies. The predicted densities range from 1.92 to 2.06 grams per cubic centimeter for Pluto and from 1.51 to 1.81 grams per cubic centimeter for Charon. These figures indicate that both entities consist of a substantial proportion of materials, including silicate rock and organic molecules denser than water ice, with a density of 1 gram per cubic centimeter, 0.58 ounces per cubic inch. It is conventional to presume that Pluto, akin to the cold moons of Jupiter and Saturn, possesses an inner rocky core encased in a large mantle of water ice. We anticipate that the frozen nitrogen, carbon monoxide, and methane detected on its surface will create a relatively thin layer similar to the water on Earth's surface. Nonetheless, such a model requires validation through spacecraft observations. The measurement of Pluto's surface temperature has proven to be very difficult. The Earth-orbiting infrared astronomical satellite took measurements in 1983 and found temperatures between 45 and 58 Kelvin. Surface measurements at millimeter wavelengths, temperatures in a slightly lower range of 35 to 50 Kelvin, 397 to 370 degrees Fahrenheit, 238 to 223 degrees Celsius. The temperature must indeed fluctuate over the surface depending on the reflectance at particular locations and the angle of the noon sun. We anticipate a threefold reduction in solar energy incidence on Pluto as it moves from perihelion to aphelion. Moons of Pluto. Pluto has 3 identified moons. Charon, the largest moon, is nearly 1/2 of Pluto's diameter. The two bodies orbit a common center of mass at approximately 19,640 kilometers, equivalent to nearly 8 diameters of Pluto. Earth's moon is slightly larger than 1/4 of Earth's size and roughly 30 Earth diameters away from it. Charon's orbital period precisely matches Pluto's rotational cycle. Thus, Charon is in a synchronous orbit around Pluto. As a result, Charon is visible from only one hemisphere of Pluto. Like communication satellites in geostationary orbits around Earth, Charon maintains a fixed position above a specific place on Pluto's surface, never rising or setting. Moreover, like most moons in the solar system, Charon exhibits synchronous rotation, meaning it consistently shows the same face as Pluto. Charon possesses a lower albedo, approximately 0.35 than Pluto, and exhibits a more neutral coloration. The spectrum indicates the existence of water ice, which is the main surface component. Unlike its larger counterpart, the spectrum does not indicate solid methane. Current investigations have failed to identify ices composed of nitrogen or carbon monoxide. Nevertheless, the lack of methane, which is less volatile, suggests their probable absence. The density of Charon suggests that the moon comprises components, including silicates and organic compounds, that are denser than water ice. Charon has a more conjectural mineral arrangement than Pluto. Researchers have utilized Charon's presence to uncover various attributes of Pluto that would remain unknown, namely its mass and dimensions. The remarkable coincidence that began 5 years of mutual eclipse events between Charon and Pluto in 1985, just 7 years after Charon's discovery, provided a significant portion of this information. During this period, Pluto transited and orbited the Moon every 6.4 days, as observed from Earth. These events transpire as Earth traverses Charon's orbital plane surrounding Pluto, occurring 2 times within Pluto's 248-year solar orbit. Careful observations of these occurrences allowed for more precise calculations of the radii of Pluto and Charon and the masses of both celestial bodies. Furthermore, observing the variations in the total luminosity of the two entities as they obscured one another enabled astronomers to ascertain their respective albedos and to generate maps illustrating brightness disparities throughout their surfaces. If their surface reflectance is similar to Charon's, Pluto's other 2 moons, Hydra and Nix, provisionally named S/2005P1 and S/2005P2, respectively, upon discovery, are significantly smaller than Charon, with diameters of approximately 60 and 50 kilometers, 37 and 31 miles, respectively. They orbit Pluto outside Charon's trajectory in nearly circular paths, akin to Charon, and within the same orbital plane as Charon. Preliminary observations indicate that Hydra has an orbital radius of approximately 64,700 kilometers, while Nix has an orbital radius of about 49,400 kilometers. Charon completes approximately 12 orbits for every 2 orbits of Hydra, resulting in a 6-to-1 ratio of their orbital periods, whereas Nix completes nearly 3 orbits, yielding a 4-to-1 ratio. Hence, the orbital periods of Hydra and Nix are in a 3-to-2 ratio. The relationship between the orbital periods displays small whole numbers. This indicates that the small moons maintain stable dynamic resonances with Charon and each other. This indicates that all 3 celestial entities consistently traverse one another and engage gravitationally, ensuring the regularity of these interactions. Pluto and its satellites were discovered. Pluto's discovery established it as the 3rd planet identified, after Uranus and Neptune, among the 6 planets seen to the naked eye since antiquity. Commencing in the late 19th century, astronomers hypothesized the presence of a 9th planet due to observable anomalies in Uranus's orbital motion, indicating that a more remote world was exerting gravitational influence upon it. Astronomers subsequently recognized that these perturbations were illusory. The gravitational influence of Pluto's small mass was insufficient to account for the supposed disturbances. As a result, the discovery of Pluto came from careful observations instead of exact predictions about the existence of a theoretical planet. The Lowell Observatory in Flagstaff, Arizona, actively facilitated the hunt for the anticipated planet in the early 20th century. Percival Lowell, the originator of the observatory and an American astronomer, renowned for his extensively reported canal observations on Mars, began the hunt. Following 2 unsuccessful endeavors to locate the planet before Lowell died in 1916, an astronomical camera designed explicitly for this task and capable of capturing light from an extensive sky area was deployed in 1929, and a young amateur astronomer, Clyde Tombaugh, was employed to conduct the search. On February 18th, less than 1 year after commencing his research, Tombaugh discovered Pluto in Gemini's constellation. The item manifested as a faint 15th magnitude star that gradually altered its location relative to the stationary background stars while it traversed its 248-year orbit around the Sun. Despite Lowell and other astronomers' predictions that the unidentified planet would be much larger and more luminous than the celestial body Tombaugh identified, Pluto's recognition as the expected 9th planet was swift. Pluto's first letters and Percival Lowell's initials make up its emblem. Photographic representations of Pluto in the United States. The Naval Observatory Station in Flagstaff, situated less than 6 kilometers from Pluto's discovery site, facilitated the discovery of Charon in 1978. James W. Christie and Robert S. Harrington captured these photos to achieve more precise estimations of Pluto's orbit. The newly launched satellite is named after the Greek mythological boatman who transports deceased souls to Hades' domain in the underworld. Before the discovery of Charon, scientists mistakenly viewed Pluto as larger and more massive than it actually is, yet they could not determine either measurement firsthand. The initial discovery photographs depict Charon as an indistinct protrusion on Pluto's surface, highlighting the observational challenges posed by the proximity of the 2 celestial bodies, their significant distance from Earth, and the atmospheric distortions caused by Earth. After the 20th century, astronomers first distinguished Pluto and Charon as independent entities with the advent of the Hubble Space Telescope and Earth-based devices utilizing adaptive optics to counteract air turbulence. A group of 9 astronomers in the United States identified Pluto's 2 minor moons, Hydra and Nix, In 2005 photos captured by the Hubble Space Telescope during a coordinated search for objects orbiting Pluto with diameters as small as 25 kilometers. To verify the orbits, scientists examined Hubble photos of Pluto and Charon taken in 2002 for surface mapping research and saw subtle yet definitive signs of two objects traversing the orbital trajectories computed from the 2005 data. The Kuiper Belt. Pluto is a member of a planar array of ice minor celestial planets that orbit the Sun beyond Neptune's trajectory. Designated after the Dutch-American astronomer Gerard P. Kuiper, it consists of hundreds of millions of objects, believed to be remnants from the outer planet's formation, whose orbits are near the solar system's plane. It is believed that most reported short-period comets, particularly those with orbits about the Sun lasting fewer than 20 years, as well as the cold Centaur objects around the giant planets, originate from this system. Certain centaurs may signify the evolution from Kuiper Belt objects to short-period comets. In the 1990s, the development of advanced telescopes and sensitive light detectors led to the discovery of the Kuiper Belt, defying long-standing assumptions. Irish astronomer Kenneth E. Edgeworth posited that Pluto's present distance did not constrain the distribution of the solar system's minor bodies in 1943. In 1951, Kuiper established a more compelling argument. He used an analysis of the mass distribution of bodies necessary for planet formation at the start of the solar system to show that there is more than one comet nucleus, or small icy bodies, beyond Neptune. In the previous year, Dutch astronomer Jan Oort posited the presence of a remote, spherical reservoir of frozen bodies, today referred to as the Oort Cloud, which perpetually replenishes comets. This remote source sufficiently explained the genesis of long-period comets, with periods exceeding 200 years. Kuiper observed that comets with short orbital periods, 20 years or fewer, travel in the same direction as all the planets around the Sun, near the plane of. The solar system requires a more nearby, compact supply. American astronomer Martin Duncan and colleagues reiterated this elucidation in 1988, which constituted the most compelling evidence for the presence of the Kuiper Belt until its direct observation. American astronomer David Jewett and graduate student Jane Liu identified the inaugural Kuiper Belt object KBO in 1992. Designated as 1992 QB1, the object's diameter is around 200 to 250 kilometers, as inferred from its luminosity. It traverses a roughly circular orbit within the plane of the planetary system, at an approximate distance of 44 astronomical units from the Sun. This is beyond Pluto's orbit, which has an average radius of 39.5 astronomical units. Astronomers identified approximately 800 Kuiper Belt objects within 12 years following the discovery of QB1 in 1992. Most are located 30 to 50 astronomical units from the Sun and must possess a diameter over 100 kilometers to be observable. According to brightness estimates, the bigger Kuiper Belt object's dimensions are comparable to or beyond the diameter of Pluto's biggest moon, Charon, which measures 1,250 kilometers. 1 KBO, Eris, has a diameter 2 times that of Pluto. We refer to them as trans-Neptunian objects because they are located beyond Neptune's orbit, with a mean radius of 30.1 astronomical units. We can identify two primary categories of KBOs, those in nearly circular stable orbits and those in eccentric elongated orbits with significant inclination to the solar system's plane. Many of these objects endure solely due to their stabilizing 3:2 resonance with Neptune, meaning they complete 2 orbits around the Sun for every 3 orbits completed by Neptune. Pluto possesses an eccentric inclined orbit and maintains a 3:2 resonance with Neptune. Pluto is typically considered a substantial Kuiper Belt object due to its orbital attributes, composition of ice and rock, and relatively modest size compared to the planets, being smaller than Earth's moon. We have designated the other KBOs with 3 to 2 resonances as Plutinos, little Plutos, to acknowledge this relationship. A minor fraction of KBOs constitutes a third category, those with extended inclined orbits that do not exhibit resonance with Neptune. Their erratic orbits can displace them onto trajectories distant from the Sun or into the inner solar system, potentially converting them into short-period comets. An extrapolation of KBO finding statistics indicates that more than 100,000 objects exceeding 100 kilometers in diameter, and likely millions of smaller objects down to 1 kilometer, 0.6 miles, 30 and 50 AU. The population may expand outward, but the extent of its reach and whether it attains the innermost edge of the Oort Cloud remains uncertain. Astronomers typically see the Kuiper belt as the outer remains of the extensive protoplanetary disk that existed around 4.5 billion years ago, which did not succeed in forming substantial planets beyond Neptune's current orbit. This is the beginning of Pluto and its moons. People commonly believed that Pluto was a former moon of Neptune that had mysteriously escaped its orbit before the discovery of Charon. This concept received endorsement because of the evident resemblance in the proportions of Pluto and Triton, and the close alignment of Triton's orbital period, 5.9 days, with Pluto's rotation period, 6.4 days. Researchers proposed that a close interaction between these two celestial entities as moons resulted in Pluto's expulsion from the Neptunian system and Triton's current retrograde orbit. Astronomers struggled to ascertain the probability of all these events, and Charon's discovery offered evidence contradicting the idea. Given that Pluto's revised mass is only 1/2 that of Triton, Pluto could not have induced the reversal of Triton's orbit. A somewhat large moon surrounding Pluto makes the escape hypothesis unlikely. Contemporary theories support that Pluto and Charon originated as 2 distinct entities within the solar nebula, the gaseous cloud from which the solar system coalesced. A similar mechanism explains the absence of methane on Charon and the relatively high densities of both Pluto and Charon. This is similar to the Moon's high-temperature formation, which seems lacking in volatile elements compared to Earth. Astronomers contend that Pluto's 2 small moons are also remnants of the collision that produced the current Charon. The other idea is that the 2 small bodies came from different places in the outer solar system and were then pulled together by the gravitational pull of the Pluto-Charon system. This appears improbable, considering that they are presently observed to be in circular coplanar orbits and undergoing several dynamic resonances with Charon. These conditions suggest that the debris ring resulting from the collision coalesced into 3 moons and possibly into additional moons that have yet to be discovered. This collision hypothesis suggests that several ice worlds of similar size to these 2 populated the outer solar nebula when the Pluto-Charon system originated approximately 4.6 billion years ago. Smaller entities, now identified as comet nuclei, have accumulated their mass. The enormous planets absorbed most of these ice planetesimals into their cores during their formation. Many celestial bodies, including the outer region of Pluto's orbit, have remained as the unaggregated remnants making up the Kuiper belt. Astronomers determined that Pluto, Charon, Chiron, Neptune's moon Triton, and various other ice moons of the outer planets probably formed as Kuiper belt objects, following direct observations of more than 1,000 KBOs beginning in the early 1990s. The Oort Cloud. Situated beyond the Kuiper belt, the Oort Cloud is an extensive, approximately spherical accumulation of frozen tiny planets that circle the Sun at distances generally exceeding 1,000 times that of Neptune's orbit, the outermost recognized giant planet. The Oort Cloud, named after Jan Oort, who confirmed its existence, consists of particles less than 100 kilometers, 60 miles in diameter, potentially numbering in the trillions, with an estimated total mass 10 to 100 times that of Earth. Despite their remoteness preventing direct observation, long-period comets, which take more than 200 years, often somewhat longer, to complete their orbits around the Sun, are believed to originate from the Oort Cloud. Ernest J., the Estonian astronomer. In 1932, OPIC proposed the existence of a distant reservoir of comets, contending that due to the rapid depletion of comets during their transit through the inner solar system, a source of fresh comets must exist to continuously replace the comet supply. Although these comets have never traversed the inner solar system, they are challenging to differentiate from older long-period comets because of the gravitational perturbations of their orbits by the outer planets at the time of initial discovery. Through statistical reasoning, Oort demonstrated in 1950 that the solar system observes a consistent influx of several new comets, which had not previously traversed the system. This flux originates from the periphery of the Oort Cloud. He discerned it by examining the distribution of the initial values of the total energy of cometary orbits. These energies are proportional to 1 over A, where A represents the semi-major axis of the comet's orbit. The original value of A denotes the comet's orbit while it was external to the solar system, in contrast to the osculating orbit, which describes the trajectory observed from Earth after being altered by the gravitational influences of the larger planets. Transits through the solar system generate a considerable dispersion of orbital energy in a negative one. Oort documented merely 19 precise original orbits of long-period comets in 1950. Given that 10 of the 19 orbits were clustered within a limited range of a negative one, it was concluded that the majority had not experienced this diffusion process due to the planets. The average value of A for these new comets indicated their origin distance, approximately 105 astronomical units. This distance also induces perturbations due to the closeness of neighboring stars. Oort concluded from the coincidental distances that comets infiltrated the planetary system due to stellar disturbances. Subsequently employing a somewhat larger data set of recorded orbits, American astronomer Brian Marsden determined that the region of the Oort Cloud from which new comets emerge, the more remote section, lies between 40,000 and 50,000 astronomical units from the Sun. At these distances, two mechanisms can perturb and redirect the trajectories of small icy bodies inward: the infrequent close approach of a star, or a massive interstellar molecular cloud near the solar system, or the gravitational influences known as disk tides imposed by the bulk of the galaxy's disk. The solar system's origin hypothesis predicts the presence and substantial mass of the inner region of the Oort Cloud, believed to begin at around 20,000 astronomical units, despite not producing comets. The Oort Cloud most likely formed from ice planetesimals that first coalesced in the outer regions of the protoplanetary disk, and then dispersed due to the gravitational influence of emerging giant planets. The extent of the Oort Cloud into space is uncertain. However, Marsden's findings indicate it is nearly devoid of material beyond 50,000 astronomical units, around 1/5 the distance to the nearest star. The heliopause. The heliopause, a teardrop-shaped region surrounding the Sun, is between the Kuiper belt and the Oort Cloud. It comprises solar magnetic fields and the outward-flowing solar wind, which consists of protons and electrons. The heliosheath, located nearer to the Sun than the heliopause, is a transitional region where the solar wind slows down to subsonic speeds, less than the propagation speed of disturbances in the interstellar medium. The heliopause tail is estimated to be 110 to 170 astronomical units, 17 to 26 billion kilometers, 10 to 16 billion miles, away from the Sun. The Sun's path through space causes interstellar gas fluctuations, impacting its structure. All principal planets, including Earth, situate their trajectories well within the heliopause. No satellite has yet attained the heliopause, although the Voyager 1 and 2 probes, launched in 1977, are the nearest at distances from the Sun of 105 and 85 astronomical units, respectively. Voyager 1 and 2 entered the heliosheath in 2004 and 2007, respectively, at 94 and 84 astronomical unit distances from the Sun. We derive knowledge of heliopause from its influence on cosmic ray particles entering the solar encounter and from the radio emissions produced when solar material expelled during coronal mass ejections traverses it.